Good morning, everybody. Welcome to our special one-day workshop on programming the graphics for audio software. This event is put on here at Belmont with Harrison Consoles. We have one of the developers from Harrison here today as our presenter. This is Tony Lassandro. I'm sure some of you have met him before. So he's going to be taking us through a day of presentations and demonstrations and many projects for us to learn some more about graphics. We will be recording this, doing a video recording. So after the fact, if you want to go back through and be able to see any of the things, that will be publicly available. We'll have several breaks throughout the day, about in an hour from now, maybe around 10:30. Then we'll break for lunch, get back together again in the afternoon. We'll have pizza here for everybody if you want to just hang out. Obviously, if you want to go and get some other food, that's fine too. I'll turn it over to Tony now and let him take it away from here.
Cool. Yeah, so I think I've met a lot of you before from Eric's class, but just to reiterate, I'm Tony, work at Harrison. I'm in charge of their plugins, so it's a lot of C++ and JUCE, and a lot of graphical stuff. So let me get these pulled up here. So I know Eric sent an email out the other day about the repo. Let's get this out of the way. So yeah, all of the materials are up here on my GitHub. That's Lassandro AN and JUCE Graphics Workshop if you need to grab them. And basically, you will want to clone it myself here. You probably need slightly larger. Okay, so you'll need to clone the repo if you don't have it already, and you will need to clone JUCE as well, which is on their GitHub. We are Rolly JUCE, and you'll need to set this up in your home directory, so whichever user you're logged in as, it'll just be within that home folder. Does everyone have the producer or needs to set that up or anything? Cool. As long as your the producer knows where your JUCE installation is, you should be good. It'll be in. Let me build it myself here. I should have it. Yep. So as long as the producer, your global paths are set to the correct JUCE installation, all these examples will work for you. Jump over to this. Cool. So yeah, today we're just going to be going over graphics in JUCE. From the component kind of widget side of how you actually start laying out elements on screen, to drawing with them, to doing image buffers and like image caching. And we also go over making your own themes and kind of being able to swap around themes for your application. So the very first part of that is the components, and this will be in the examples folder. Put myself here. Cool, so we'll be working from the first examples folder. The components in JUCE are basically just their base element class for any kind of UI widget. So it's just a drawable element on screen. It accepts user input, so keyboard events, mouse events, all those kind of things. It has different elements to it, basically like you can set its name, you can set certain properties for it, it has a visibility, it's whether it's enabled or not. And because they're on screen, they all have size and position information as well. And they all maintain their own child hierarchy. So once you start adding components to the screen, it'll start out with a base component, and you just add subcomponents to that. Keep track of things that way. JUCE includes quite a few default widgets. We won't really be using them today. Ours kind of just goes over the basics more of like layout and some of the event handling and stuff like that. But included in JUCE are, they have their drawable classes, which are kind of the most simple component. They'll have like a drawable rectangle, drawable paths, stuff like that. And really it's mostly used in their SVG loading, so you can like take a vector image and just tell JUCE to start rendering it. But I use those sometimes when there's just simple elements you want to draw on screen that you don't want to go in and like mess around with some whole giant paint function trying to put stuff in. So those are probably the most simple ones, aside from the base class of component. They include a lot of default widgets that are used for your application. So the sliders, buttons, labels, those all have callbacks. So once you start actually interacting with them, you can control the logic of what they actually do, of when the button is clicked, when the slider's dragged. There's some more complex views, usually the hierarchical views of like a tree view or a list view. And those are interesting. You kind of manage it in like a model view way where the component itself doesn't do a whole lot, and you have to attach a model with it that actually controls when the component is looking for information. The model will tell it, here, are the cells that you're going to show in your list view, and here's how you draw them, here's what the names are. So those are kind of split up a little bit, and the rest are usually just containers and windows. Viewport is probably their main one. I don't know if there are other containers. But the viewport, basically, you just add sub-components to that, and you can use it as like a scrolling view, and zooming and all that good stuff. Cool, so let me switch over to the first example. This will be in the examples folder, number 1, basics. So if you have the ProJuicer open, when you click open, file open, if you select any of these header files that are in the examples, they're all in JUCE's pip format, which basically just means there's a big comment at the top with a bunch of metadata on how to build a project. So these will open up. And when you go to this tab right here with the little wrench and screwdriver, that is JUCE's live build engine. If it's not installed already, there will be a button right here saying, please install the live build engine, so you can just click that. But this basically just runs Clang behind the scenes and builds your whole project for you. And once it's done building, it will show all of the components that it found in a little list here. Cool, so once it's done, it'll show all the components. Obviously, JUCE has a lot of them, so it actually shows you the whole JUCE list of what's available. But for our purposes, we usually just only have a demo component. And you can click play on that, and it will pull it up in its own little window and show you it, and allow you to resize it. So that's how we'll be running the examples for today. This first example basically just goes over, I can't get that window back. This first example basically just goes over the kind of component basic API. So as we said, you can set names, you can set component IDs. Both of those are things that you can use either for drawing. I like to set names and use them for drawing a lot. Component IDs are good if you want to be able to just have a bunch of different components of different types and be able to just reference them by the same name. So every subclass of component, you can access all of these properties just through that base interface.
So did anyone else get a bunch of error messages?
That's what I was worried about. Yeah, there have been some weird quirks with the live build stuff.
I've been having those for 2 weeks since
Yeah, are you also on dark mode? Yeah. Yeah. So if anyone has issues with the live builder, that seems to be a JUCE problem for right now, or a pro juicer problem. But if you do have Xcode installed, you can click on the little Xcode button up here, or Visual Studio if you're on Windows, and you can open it in the IDE, and all of the errors will go away. Basically, it's just within the live build engine, there's still a few problems. Yeah, so here we kind of do what I mentioned before. The actual paint routine of this component utilizes its name, so we're not having to like save our own state and stuff like that for that. Components have enablement, which I mentioned. So here, there's just a little commented out block of set enabled to false. But if we change it to 1, our paint routine is checking whether or not we're enabled. So when we're not enabled, it'll just draw in a red color instead. Rebuild. So that's always useful for kind of conveying to a user the state of which a component can be interacted with or not. For example, in our plugins, I think every single paint routine basically checks whether something is enabled or not. To set colors darker, take out any saturation, basically just evoke the sense of like you can't click on this. JUCE will do that for quite a few of the built-in components, like if a slider, buttons, and stuff like that are not enabled, they actually just draw them with a layer of transparency. So it kind of gets the same effect of where you know something is different about it and the component looks darker, and when you mouse over it, nothing really changes, you can't click on it, all of that. So
Is it possible to make your font larger in the Producer?
it should be.
Actually, I don't see where that would happen.
Yeah, if not, I might just open these in Sublime or something. I wonder if they do. Producer, code editor, font size. If you edit the color scheme, there we go. Strange place to put that. There we go. That's a lot better. Now, is the color okay for everyone? Is that kind of washed out with the light or anything? Oh, cool. Perfect. Cool. So yeah, basically these just provide the base interface that you need to do anything UI related. So enablement, visibility, all that kind of stuff. Here we also use, every component has a properties set, which is basically just a big hash map. So we set a property that we call greeting, and we set it to the string hello world, and then we can just use that later on from the paint method. So down here we grab the text of get our properties, get the key that is called greeting, and we make it a string, and then we just concatenate all this together. So the text is I am, and the name with the greeting before that. So we can change that, take that out, and rebuild. And now there's no more greeting. So that's useful when, and we'll get into this a little bit later, when you're doing themes and stuff like that, but you start using your own custom components, if you want to still be able to access all this stuff without having to typecast back and forth all over the place, the properties set is always there, so you can just pass things around as long as you just use the same identifiers for everything. So that's useful when you do the look and feel stuff and you're using custom components. All you have to do is just say, does this component have this property or not? And if it does, you can know that it's one of your custom components and that that property was actually set for it. And like I mentioned, every component has bounds. This is covered in a later example, but here we just set the size. So our component is going to be at 0, 0. And since it's our root component, you really won't ever have a position for it. If it's a window or something and you want to move it around on screen, you'll actually set a position or tell it where to go. But for the main content that's going to be within your window, usually that's just going to be at 0, 0 and just have a size and grow left and right. So here we also do the visibility. So when our component's actually added to this window, we can say set visible false and nothing will show up. So when a component is visible, that's when it will actually get painted and actually be able to receive events. But if it's not visible, it will not be allowed to do either of those things. And if it's not enabled, it usually won't be able to receive events. And then yeah, so our first paint routine is basically just that. We check enabled, we use that to set the background color. We fill the entire bounds with this get local bounds, which basically just returns that size to you with a position of 0, 0. So that's really useful when you are painting a component or laying out a component's children, and you know that you're working within the relative bounds of that component. So you can just say, we're only working within this rectangle, so let's not take any position information. Just get local bounds and then start manipulating the rectangle from there. And that covers the basics of the component API. We'll get into a lot more of the specifics a little bit later. So component painting, when JUCE is ready to paint things on the screen, basically it just allocates a big buffer of the size that it actually needs, whether that's your entire screen size or just 1 or 2 windows that you might have open. It'll allocate that space, and it'll start with the top level component, usually a window or something placed directly on the desktop, and we'll just traverse that child hierarchy of the components and start calling those paint methods. And like I said, each one has to be visible on the screen to actually be drawn. And as it's drawn, your component's paint method will be called first, and then the children will draw over top of that. But there's also methods to just be able to go over top of the children and kind of draw overlays or whatever you need to draw on there. And I use that sometimes when it's a little more cumbersome to have extra components in the hierarchy, like, oh, I want to draw this one little piece over top of these other things. It's a little easier just to say, okay, I'm just going to go and draw over the children rather than trying to make another little component and stick that on top. So when you are actually painting, you re-trigger those events by calling the component repaint method. And the most important thing to remember about the whole system, since this is software rendering, is that none of the painting happens synchronously. So when you're actually telling a component to repaint, it's really just giving a message to the operating system saying, hey, there is a rectangle, this far along in this window, and at some point it needs to be updated so the user can see what's going on. And you can call that for just the base repaint. If you call that, we'll just repaint the whole component. So the whole bounds on screen will be marked to the operating system. But you can also just repaint sections of a component. So if you have just little pieces that are moving around within a component and you don't need to redraw the whole thing, you can just call repaint and give it a little rectangle that it has to paint. Basically, all of these get coalesced by the operating system, so at some point it will just have a big collection of rectangles that it knows are dirty and need to be updated, and it'll put all that together and say, okay, this is the minimum like screen size that I just need to refresh. So it'll go through that and have everything draw again, which in this case will tell JUCE, hey, this whole section needs to be redrawn. JUCE will figure that out, allocate that that pixel data for you, and then request from your components, repaint just in this region kind of thing. So it's important to note too that if you start calling repaint a lot on components, the OS is completely free to just deprioritize those calls and throw them away. So if you are doing something like trying to draw some sort of dynamic display at like 60 frames a second, which would be pretty common in audio software, but if you're doing it on the software side of software rendering like this, where it's not OpenGL, not dealing with the GPU, stuff like that, the OS will very likely just throw away your repaint calls if it knows it's getting too heavy and that there's like too much other stuff going on. So, and I've seen that a lot where basically if you are repainting regularly, you will just see a huge FPS drop. And if you're doing other stuff like repainting just in sections and it starts throwing stuff away, for example, if we had like a ball moving on screen and you wanted to repaint the old position and the new position so that it properly updates, sometimes you will see one of those get thrown away, so now suddenly there's a copy or 3 copies of that same little rectangle over because it didn't repaint the old section and it only repainted the new section. So that's important to note, and it's usually avoided if you use components instead of doing like one big component and trying to manage a bunch of repaint calls. It gets a little tricky, but JUCE, if you are using the component system, handles it a little bit better, but it's still something to be aware of if you're regularly repainting. And that brings us to the second example. Let me pull that up.
Are there any questions so far?
Yeah, feel free to ask any questions in the slides or in the examples at any time, basically. If it's smart enough, I should be able to drag a file. Nope. So I gotta go open and go all the way back to my folder. Here we go, component painting. So in this example, we basically just start out, and you'll see this a lot in the examples. We just make a component that's a square, and it takes a color, and when it's drawn to the screen, it just fills its whole bounds with that color. So we use that a lot for these demos. So as I mentioned, paint is called first. Then JUCE will traverse that child hierarchy and call things. So here, we give our size for our main component. Let me make sure this is building right. We set the color for the square. Here we just make it a red hue. We add and make visible to the square. So that's how you actually start using the child hierarchy, is the components have add child, add and make visible, a couple different methods that basically just say, I want to make this a child component. And a lot of them let you do something else. So in our case, add and make visible will just always add the child, set its visibility to true, since it starts out false, and you'll have your component drawn on the screen. There are other ones like add and set component ID and stuff like that. Not used quite as much, but still kind of handy when you need them. So since our size is 500 by 500, we just, after we add the square as a child, we call center with size. So it gets and calls its parent, finds out what size it is, finds the center of that, and then just offsets it. So our component square is 250 by 250, placed directly in the center. So here we will be drawing the background.
Why is, excuse me,
Hmm?
why is the center with size after the add and make visible? Why wouldn't it be before that?
It actually has to be in that order because center with size relies on really two things. One, the component having a parent, and two, the parent having a size itself. So usually in these demos, I was making it like, oh, I'll just add all the components and then like set a size at the end. But there's a few quirks with if you just want to like set everything up from the get-go and do all the layout kind of there, that sometimes you have to reorder stuff. Like in this case, we have to set the parent size, then add a child, and then finally like actually start laying out the child if we want to use the center with size.
So is that something you just kind of learn from experience? I mean, or is it documented that way? Or?
It is documented.
Okay.
Usually they are pretty good about that. So we should have this open while I'm here just in case. So center with size, and there's also set center position and stuff like that. So we could have actually done that as well. If we set the center position, which would basically just be 250 minus, half of our square size, then that position would actually be the same once we've added it. So then we could just say...
So that was an alternate way of doing it, is put that one in front if you wanted.
Yeah, exactly.
Okay, I see.
So yeah, and that's one thing to keep in mind too, especially if you do the layout like in the constructor of a component, that sometimes it's a little quirky and you like have to set up things beforehand or before everything is really on screen and has sizes and positions. But if you set a position for a component and it doesn't even have a parent and the parent doesn't even have a size, the position will stay with that component once you actually add it. So you could just go through and set all positions up beforehand. But some of them, like center with size, requires it to be within a parent.
Yeah, okay.
And there's a few other ones actually that rely on kind of having that hierarchy set up already.
So set bounds relative is the same, yeah.
Exactly, yeah. So if you set the bounds relatively, you'll have to have a parent first. And you'll want to make sure that that parent has a size, because if it is the other way around and you have a lot of code there, you might end up with like, why isn't my component showing on screen?
Was there any visual glitch because of it, or does it actually have to wait until that's done before it displays? Or the add function should display it on the next frame, right? And
yeah.
Then so you have one display, and then the very next frame it changes.
Yeah.
I mean, do you see a flicker or any kind of?
It kind of depends. Because we're setting this all up in the constructor, nothing ends up getting shown until the whole demo component is constructed, and then JUCE. In our case, when we actually click play, it makes one, and then it makes this whole other window around it. So we actually have a lot of components going on here. Like there's some extra buttons and stuff like that.
So the larger components are ordering these commands.
Exactly, yeah. So, and that's one good way to go about it usually is like do as much setup as you can within a constructor. For that reason of when you want the, in our case, our demo component to actually be on screen, here is the state that you can expect it to have. Because the constructor had to go and run completely before JUCE was allowed to take that demo component and add it to a window or do anything else with it. So sometimes, like you said with the flickering and glitchiness thing, sometimes you can run into that if you're doing a lot of these kind of layout or like visual changes at runtime. So if you're like adding components around and doing stuff that way, you can run into some weirdness. I guess it depends on how much work you're doing. If you're doing like a huge heavy load and you're like trying to add all these components to the screen and the OS is like, we're not going to repaint that much of the screen, you might run into some weirdness. Usually it's not too bad, and using the components and not calling repaint kind of works out. I haven't quite got to a point where there's been like too many things trying to be added to the screen at once that I see like weirdness of the OS starts like throwing away things and stuff like that. Cool. So, as I mentioned, we basically go through. We paint our main component with this blue, and we use the same thing of get local bounds. We reduced it a bit to just give it an offset. So it'll take 50 off from each side, basically, and then draw within that area. So here we have our sky blue. We have our red square component, which is going to be drawn over that. But we, in our demo component, override the paint over children method, which basically just gives us free reign over the whole bounds of the demo component to draw over top of the children. So you can basically visualize it as like paint gets called. There's an extra step like in the middle here where all of the children go through and like they get painted and their children get painted and all of that. And then after all of that happens, we can call paint over children. So we paint and we draw our text over it, and it just shows up directly over top of the child. And whether or not you need this really depends on what you're doing. I think I've only used this in a couple cases where, like, in our multiband compressor, we have an OpenGL component drawing some RTAs and some crazy stuff on screen. And it was a little cumbersome to be adding components to that. So we actually use the paint over children to just align each section of the multiband compressor and draw our text over top of that. So the 1, 2, 3, 4 labels and those kind of things. That is,
Tony, on that one, I
Yeah.
understand how we're drawing the blue rectangle, and I can see where we're defining where we're going to have our own square component.
Mhm.
But what I don't understand is where the paint happens for that square.
Right, so here in our square component, we override the paint method. And it basically ends up that we don't have to manually call paint for the child components. So, and I think we stepped through this in another example too, but basically, I kind of wish we had debugging right here, because it would be nice to show that. But basically, once we start drawing the demo component to the screen, JUCE goes in and grabs us a chunk of pixel data that's big enough to hold this, and it first calls this paint function. And if you were to look at the actual component code, you can see the loop of like it calls paint and it passes off that context that is drawing into that that pixel data, and then it just looks at every child component that component has, and it calls. There's a method called paint entire component. Which actually, let me pull that up right here. So this paint entire component, if you were to call this, it essentially does the same thing, and this is what JUCE calls under the hood to set everything off, is that, and it even says you should very rarely use this method, but it calls paint, kind of has it in reverse order. It says it calls paint, paint over children, and recursively calls. But basically we start out with that paint call for our demo component, then every child has this paint entire component called, and all of that is drawn on top of the original paint contents from the demo. And after every child has painted its entire contents, then we go in and call paint over children, and we can draw over top of all of that. So it's basically just a lot of layering of, we start out with the blue, this first, or this only child, the square has paint entire component called, and because the square doesn't have any children or anything, all it has to draw to screen is a red square. But if we were to add another one, say we have like a square 2, and we make that dark color. And if we add the square 2 to the square itself, let's say it's 25 by 25 in the left corner. Rebuild. Oh, no.
It's not going to like that visible.
Visibile. I think I mistyped that almost every single time. I want to add too many eyes all the time.
Needs one more eye.
Yep. That's where it goes. There we go. So then we can just start adding, and basically, this second square, this tiny little black square, is only seen within that loop of the child for the paint entire component thing. So it goes through, calls paint entire components on the red square. So it'll draw all of the red first, and then because we're painting the entire component, it needs to go through its own children and calls paint entire component for those as well. So it basically steps from main component, paints itself, we go to the first child, this paints itself in all red, go to the first child of that, this paints itself, and they don't have anything else to be drawn, so we step all the way back out to the main component, which has a paint over children method, and we just draw the text over top. And that goes over top of all the layers, basically, that were in between that paint and paint over children method.
So the add and make visible is where we are adding it to be a child of, in the first case, they're the main component. And
Yeah.
then in the second case, we're adding it to be a child of square. Is that how I should
Exactly, yeah.
understand that?
And sometimes these are a little funny to read, especially when you start having a lot of base classes that you're deriving from. So here, because we're just calling it within the constructor, it's pretty much equivalent to if you said this, add and make visible. But in C++, we usually don't use like this or have like a self thing. I know a lot of other languages do that. It would make it a lot more clearer, actually, if we did. But basically, yeah, for the demo, we say add the square to this and then make it visible. And then later on, we can just take the child we already put in the demo and say, hey, square, now you're going to have a child as well. That'll just be a little black square in that top left corner. Scrolling is a little haphazard on this thing. Let me go to trackpad. I don't think I have scrolling speed on the trackpad or something. Cool. Are there any other questions about the painting loop and how all of that gets called, basically? Cool. We'll go into the slides again. I think we have one more slide before the third example. So this kind of just reiterates a lot of what we said. Components can have many children, so you can add as many components, I guess, as much memory as you have. There will be some sort of limit if you add, 20 billion components or something like that. But each component should only have one parent at a time, and that is enforced by JUCE. So if you start adding a component to something else, if I recall, it either throws some assertion, like it'll just stop the program and tell you, or it will just actually silently transfer that ownership. So now it removes itself from its original parent, adds it to the other parent, and everything's all good. Components normally cannot draw outside of their bounds and their parent bounds. So when we say, in our last example, all of the square components basically just called fill all, and that fill all was the same as if you were to say get local bounds. We just grab the size and fill a rectangle of that size. When a component is being painted, the graphics context is only working within the bounds of that component and will not draw outside of that. And the same goes for the parent. So, and we cover this a little later too. When you're stepping through, for example, in our blue and red square example, that first region that the context is like restricted to is going to be the size of your demo, and then it reduces that region to the size of the red square. So So when you're in the first paint call for the demo, you cannot draw outside the bounds that that demo component has. When you're in the second paint call of that red square, you still can't draw outside the first bounds, but you also can't draw outside of that red square's bounds. Now there are some flags that you can actually just turn this off and be allowed to draw anywhere, but you'll run into a lot of problems with that in regards to the repaint stuff I mentioned. Because when you call repaint on a component, it'll still take its bounds. But if you disable all of this and you say like, okay, I'm going to draw a square and I'm going to draw some random thing out here outside the bounds, and you repaint, that random thing will not be updated. So usually you just want to keep the default behavior and say, every time we're drawing a component, we are only drawing within the rectangle that encompasses that component's size. The other thing to note is that if you delete a component, so say you heap allocate it and you just randomly call delete on it sometime later, it will remove itself from the parent. So you don't have to worry about like, oh, I deleted this component, but I didn't like remove it from the parent and take it out of the hierarchy and everything. A lot of the component stuff in JUCE is set up to either do this automatically for you. Something like, I should remove myself from the parent if I'm being deleted. Or it uses reference counting. So when you do delete a component, there will be some sort of like weak pointer or something like that, which usually you see in Java, not quite as much in C++, until C++ 11. But usually it doesn't come down to any kind of like problem if you delete a component but like someone still is like looking at it, unless you're using a raw pointer. Basically just, we have that square, we take the address of the square, and then we just hold on to that forever. We would have to either invalidate that pointer or something else to actually know that that is not allowed to be used anymore if we are deleting our square. But yeah, usually you don't end up deleting components unless you have some sort of dynamic UI where there's a lot of things being added to screen that are based off of some thing the user is doing. Like say we have a bunch of buttons that we add based on like how many tracks a user put on the timeline or something like that. But even in some of the other components like the tree views and stuff that I mentioned, those are dynamic, but they actually don't require heap allocating a bunch of components. So usually you don't have to worry too much about it unless you have to have some sort of dynamic setup that requires you to start heap allocating components. That was all for that one, and this example is pretty short as well, if I remember. This component hierarchy one basically just goes over a little bit of what we had last time. This time we have 3 squares, same square setup as before. And we have 3 of them, red, blue, and green squares. We set their colors. Same thing here, where we're calling center with size after we set up a size. So we make the red square in the center with 250, 250. We add the blue square at 125 by 125 size and 125, 125 position. And we add that to the red square. So the blue square will be drawn within the red square. Green square is just a 50 by 50 thing at 0, 0. And so, kind of like I said, we just have 3 squares. If we make this blue square a lot bigger, so suddenly this one is like 500 by 500, we do not see, once this rebuilds, there's not going to be any change, basically. Because we're already offset at 125, 125, you only have this much space to draw before we run into that graphics clipping thing that I mentioned before. So once we're inside of this component, we only have that much space to work with. So if you try to draw some huge component, you better either resize that smaller or make sure that it's in the right position, because it will just cut off the side of the screen otherwise. And as I mentioned before, all the bounds are relative to this, so this red component can be anywhere on screen. But when you are actually drawing this blue component, that 125, 125 will always be relative to the top left origin of its parent component. And we can see that with, there's a little thing here where we take the green square is normally added to the red square, change this to 1, and we can see that it's added to the main component. But because it's 0, 0, it jumps over to the actual top left of our window instead. So yeah, basically just to reiterate, just everything is always relative to the parent. So when you get into more complex layouts and stuff, you just kind of always have to keep that in mind of if you want something to be shown in a specific spot on the screen, everything will have to be set up in a way, especially if you have like a deep hierarchy, everything will have to be set up in a way that your final bounds that you're calling, for example, are like 0, 0, 50, 50 bounds here. You will need to make sure all the parents are in the right spot to actually get this to this specific spot within the window itself. But yeah, usually it doesn't come down to that. Sometimes in the audio realm, it does a little bit. A lot of the like skeuomorphic interfaces where it just looks like an actual picture of the gear and stuff like that. Things are kind of in loose spots. There's not like grids or any kind of that layout. So sometimes you get into that where it's like everything is just one big parent and you just add stuff in and you just tweak it around until it looks like it's in the right spot on the screen. In a lot of other layouts, usually things are kind of grid-based or have some sort of structure of like, okay, we're going to take this specific area, split it into 5 sections and lay out everything where the relative sizes and stuff like that. And we get into that a lot later too. For now, it's mostly just hand positioning everything, which you might run into if you are doing audio plugins. That all kind of depends on the aesthetic, really, I guess. Isotope, for sure, they use all kinds of crazy layout systems, considering they have so much going on at screen, and they have tabs and all kinds of navigation stuff. Are there any questions about parent hierarchies or positioning and that kind of stuff? Mm-hmm.
Like if we had a call to later delete one of the parent, like the red square, it would delete the other ones as well.
Yes, if you... I might actually have to check on that, but I'm pretty positive that is the case where basically when you are calling delete, and we can't do it here because since this is actually just allocated with that demo component, it's not allocated on the heap, so it wasn't made using new or anything like that. But if we said this was like pointer to a square, which we might have to change some stuff, but I think we can. Red square equals new square. Is my biggest annoyance with C++ is the arrow syntax. I have to go and change every single dot to an arrow. There we go. So if we were to actually just run this right now, we probably won't see anything because the Pro Juicer doesn't have debugging, but if we just close this window and let that red square just never be deleted, JUCE will tell you. And if you do call delete on it, what ends up happening is, since we're using the actual operator delete, C++, the first thing that will get called is the Destructor of square, which in this case we don't have. It would usually look something like this, and we could say something, like we're destroying the square. So you can do whatever you need to like actually clean up stuff, but because this derives from component, the destructor for the base classes, it traverses back up. So in the destructor of the base component class, it will do any cleanup that it needs to actually handle that. And I believe that it actually will not I don't think it can delete the components because it wouldn't know whether or not, in our case, we have the red square as a heap allocated component and the rest of them are not heap allocated. So it won't call delete manually. Won't call delete automatically for you. But if you were to delete the component, it will handle, not seg faulting and stuff like that. Like this demo component will not have a pointer laying around to the red square if all it had was, we heap allocated a square and we said add and make visible, then we delete it later. The demo won't crash, trying to paint a component that like was already deleted or something like that. But the rest of it, if you are heap allocating a bunch of components, you will have to manage the lifetime of their memory, so to speak, which usually you can do with a lot of like C++ 11 and on like smart pointers, like having unique pointers to something. Once that unique pointer is gone, it will know to just clean up the object for you. So a lot of times if people are doing dynamically allocated components like that, they will just they'll have some sort of array or just members within that parent component that they set manually that have the that smart reference to it. So once those go out of scope and that parent is going away, it will clean up all of its child components too. And JUCE offers some stuff like that too. JUCE has been around since like 2004, so actually they have a lot of kind of redundancies with the with C++'s more standard library. So there is this owned array class that you can use if you do need the parent to actually be managing the lifetime of the children. You can just have an owned array that every time you're adding a child, you just also add it to this array. And once this array goes out of scope, aka the parent that has the array is deleted or goes out of scope, this will go through and clean up all those objects for you. But yeah, just by default, if you are deleting a component, you will have to clean up components or any other kind of data members that you may have like heap allocated along with it. Are there any other questions about that, or questions about how the parent kind of manages children in that way? I think this brings us to graphics, which will be the second example folder.
Well, are there any cases, Tony, where just using the standard classes as designed by JUCE, where you can end up with a memory leak, just using it as designed?
Absolutely. There are actually a couple cases that I found, because there's some weirdness with how JUCE lays out its API. And a lot of like standard C++ stuff, or I guess more modern C++, not necessarily the standard library. But you will see stuff like if you are passing off an object to some sort of API or function.
So I mean like late binding? Is that what doing?
Not late binding, but it will take the argument, instead of just a pointer to some object, will usually be like a unique pointer or like a shared pointer. And they use that to basically tell you or evoke that when you're reading that documentation, this is taking ownership of this object. So when you hand over the pointer to a square or something like that, our square component, it is done under the knowledge that it is passing off a unique pointer. So when that unique pointer is finally gone, the object that you passed off will also be deleted. And JUCE does not do this. So there's a few examples where, like, for example, there's this positioner class with JUCE components, which really is not used that much at all, but it, under the hood, uses kind of the same thing as a unique pointer. I think it uses its own JUCE variety of it, but when you set a positioner, it will be, if you have one there already, it will be deleted. And if you just set one once and never worry about it again, when that component goes away, it will actually go in and delete that positioner as well. But because they don't, really because it was written so long ago, before unique pointer and before a lot of the more modern C++ stuff, it doesn't really tell you in the function signature itself that this is taking ownership of the object that you're handing off to it. So in this case it does, and the only way that they tell you is by actually writing it out in the documentation. But there's other ones, like this set look and feel. When you set a look and feel, the object is not deleted by the component. So it all kind of comes down to just having to read the documentation for every single method, or crash and figure out, oh, something went wrong, and then go through the documentation and find out what happened. But usually JUCE will tell you as well, like if you, for example, and I think this comes up later in one of our demos, if you set a look and feel and you don't set the look and feel to null pointer when that component is going away, so say, you know, our demo component, we set some custom look and feel object, which is not going to be owned by the component. If we don't set that to null pointer, when that component is being destructed, JUCE actually just asserts on you and says, like, hey, you shouldn't be like keeping around, you know, a reference to the look and feel when the component's still, you know, being used and stuff like that. There's a few quirks to it basically, but it kind of comes down to just the API and whether or not they decided to make something owned or not. But it does not tell you in the function signature. So it's usually all up to reading the documentation. So the positioner is one. I believe there's a few examples like this component effect, which the image effect filter class is basically just a thing that gets past an image and a graphics context, and then you can just apply whatever you want to it. So JUCE actually uses that for like drop shadow effects and doing like glow effects and stuff like that. But when you set a component effect, it takes a pointer again because it has to know like this is the one that I'm actually going to use, and it doesn't make a copy of the image effect filter, and it can't take a reference to it, so it has to use a pointer. But it doesn't delete the object, so you could have one image effect filter that's, you know, the global drop shadow or something, and every component has a pointer to it. But if you dynamically allocated that, you better delete it when you're done, because the components will not handle that for you. So that's another one that does that, but there is there's one more in here, at least I know that. Set cached components image will be owned by the component. So there's at least 2 or 3 cases in the component API where when you pass something in, JUCE is deciding it will actually take ownership. So it will delete that out from under you. So it's just something to be aware of. The graphics side. Cool, so as I mentioned, highest level component that you can have is one that's directly on the desktop. That will always be a window, even if the window looks like it's a native window, like a Mac OS window kind of thing. It is actually still a JUCE component, and it just has a window that it's like controlling. You can also place any kind of component directly on the desktop. We could actually take the demo from before with the squares and stuff and just say, stick this on the desktop, and it won't have a window handle or anything. It will just be the blue square and the red square just sitting right there on your desktop. So, as I mentioned before, we go to the highest level one, usually a window or something that's full screen or on the desktop. Paint gets called, traverses all the children, paints over them if it needs to. So that was kind of going through. So what actually handles the buffer of pixel data that I mentioned before is the graphics context. So when JUCE is ready to start drawing your user interface, it will allocate some chunk of pixel data large enough to hold all of it, or it might even use just some buffer that already exists and it's just reusing it. And what it does is passes you a graphics context that basically gives you an easy API to draw into that. So all of the JUCE graphics are vector graphics. So when you're actually using all these draw calls and stuff, you're working within points of like, I'm going to draw a rectangle, that's at this position. I'm going to draw a path that draws a little squiggly line here. And you don't have to go through and say, set this pixel, and draw the whole thing out pixel by pixel. You basically just pass in lists of points that get turned into path operations. And way down in the graphics stack, all of those paths get collected up and rasterized. So JUCE ends up doing it that way, where it just goes through literally line by line and figures out, okay, where am I hitting a path? Where do I need to draw a rectangle? And that's how it also handles the anti-aliasing. So when it's going through line by line and you have like a smooth curve or something, it knows, okay, I need to feather these edges out as I'm hitting into them, so that the smooth curve is not super janky curve, but actually looks smooth and continuous once it's on the screen. And the important thing to note too is that JUCE handles the resolution aspects of your operating system. For example, I'm just running on like an older MacBook, but the stuff that I work on at work uses like a Retina, so you have a higher pixel density and the resolution is like way, way bigger. But all that you have to really deal with, you don't really deal with pixel sizes, but you just get coordinates. And those coordinates and that size will map to the appropriate pixel density once it's actually going up on screen. So if I say, draw a 500 by 500 square, that really means something different on my laptop versus any of these iMacs, where the pixel density is like 2 or 4 times larger. So the graphics class basically handles interfacing with all of that. And the way it does that is the base is this JUCE low-level graphics context, and that is the implementation specific. It handles basically the implementation of doing all of that path collection, rasterizing all of that, putting that on the screen. And you'll see them as like, there's a low-level graphics context for there's the basic one, which is the software renderer, and that's what's used on Windows and Linux. So when you're drawing on those, you'll actually see the exact same image no matter what. You ever take, pixel density and resolution stuff, but the same code that runs to draw graphics on Linux and JUCE also draws the same graphics on Windows. On macOS, you can toggle whether or not it's actually using Core Graphics, which is Apple's own graphics class or graphics API. And Core Graphics is basically the same way. It's all just vector graphics. It's a lot more powerful and a lot more expansive just because it's Apple's operating system library. But the low-level graphics context is what wraps over that. So every time you're saying like draw a path and you're using Core Graphics, it will just actually go through the low-level graphics context, and that will tell Core Graphics, hey, I have a path here, I need it drawn to screen. It just passes it off, and Core Graphics does the rest for you. Some other implementations, you can basically do whatever you want once you have a low-level graphics context. There is one that handles, I believe, PostScript rendering or something along those lines, and it's kind of setting up vector graphics in the same way that a PDF is constructed. I wrote a low-level graphics context thing that just maps back to SVG files. So you can say draw a path and draw all this stuff, and instead of drawing it to screen, it actually just writes it out as an SVG text document. So you could stick one of the SVG low-level contexts in to some big complicated user interface that's already been designed, and it'll spit out just a big SVG that is that exact thing. And it's actually useful for, we were using it a little bit at work for two things. I was using it for a lot of the plugins that I started out working on were ports, so I would just make it look close enough to the old one, and then I would actually just do the SVG thing and like tweak it around from there. So it was a lot easier to design knowing that like I'm starting from this base, I'm just gonna push this out and then like mess with it in Illustrator or something. But it's also great for screenshots. If you, instead of doing like a screenshot, you could just have the SVG of your whole user interface and just have that in a browser or something like that. But suffice to say, you can kind of do whatever. Once you have the low-level graphics context, you can map all those graphics calls to whatever you need it to actually do, including that's how JUCE accomplishes its OpenGL implementation as well. Cool, so we are in the second folder now. Cool, so this first demo, we have a square again, but instead of drawing a consistent color, we are going to take a random color. So basically we just generate some random integers and make them uint8 for the RGB values for the color. And we fill an ellipse instead of a square this time. So I'm actually not sure why I called it square. Should be ellipse. This demo, this basically goes over the repainting. So there is a method in the component that easily lets you just toggle whether or not a component should repaint when you're doing mouse events on it. So if you enter or exit the component, if you click or double click on it, and when you let go of the mouse, if this set repaints on mouse activity method has been set to true, the component will know, okay, I'm going to redraw my entire contents. And that's useful if it's like you don't want to go in and make a subclass that does all this. And I should also note, because it's mouse enter and mouse click and all this, this will have a lot of flashing colors. So if you're sensitive to that, do not go in and spam the mouse button. Probably should have put this on a timer, actually. That's like only every second it will change, not as fast as possible. But this basically goes over. We draw in. Whoop! Okay, that was strange. We have found some sort of bug. I wonder if that's because of my laptop being on the display or something.
It's happening to me too.
Oh, that's weird. Wonder why that would be. But yeah, basically, every time you click, you get a different color for both. The important thing too is that if you are only clicking on the circle, you will notice only the bounds of this are being repainted in the circle and in the parent. So the circle only draws this ellipse, but the parent is drawing the color behind it. So once this component is being repainted, it has to go to the parent and also say, anything that is drawn behind me needs to be updated, because, in our case, all of our corners are shown. If you don't do that, like for example, if this was our regular square component and we were just filling the whole bounds, obviously you can't see anything behind that component. And to tell JUCE that that is the case, you basically mark a component as opaque. So if a component is opaque, let's rebuild. When a component is opaque, you will notice that the corners are never being repainted because we are not filling these parts of the component. We're only drawing that circle in the middle. So it started out with the very initial color that it had, which was this orange color. And unless you go in and actually fill the whole bounds again, that will always be there because it's just still sitting there on that screen buffer behind the scenes. But if we were drawing a square, when the square itself repaints, when that child component repaints, the parent doesn't have to go in and draw itself again. So you'll notice this area that's behind the component doesn't have to be updated. And this will actually save you a ton of work in CPU cycles, basically. If you are already drawing, say, like a meter or something where it's already a square and you can't see behind it anyway, any component that is the case for, you should mark opaque. Simply because you don't want to be like redrawing all these background contents that you can't see anyway. But yeah. And that kind of exemplifies that hierarchy too, where we have to go in and draw the background first, then we go through the components and draw those. Are there any other questions about that? I think we're going to be moving away from component stuff now and more into the actual graphics context. If anyone has any component questions or anything.
I think now might be a good time for our first break.
Cool. So yeah, next step is basically just moving from the component stage and kind of how the layouts are put together into the actual graphics context. So as I mentioned before, it's basically just a nice wrapper around drawing into a big pixel buffer using vector graphics only. And it provides a lot of like helpful methods of drawing shapes. So you may have seen some before of like we were drawing rectangles or doing a fill all, drawing rectangles, drawing ellipses, that kind of stuff. It basically gives you a bunch of those methods to just easily say, I just want to show this shape on screen, just set the color and like, you know, draw it to the screen. And it provides a few, like there's every fill method, like fill ellipse, fill square, fill rounded rectangles, that kind of stuff. And those usually provide like an outline as well. So when you're calling like fill rectangle, obviously you're drawing the whole thing just within that bounds. There are other ones like draw rect will just draw an outline of a rectangle, but it'll draw it to those bounds so that the outline is like centered on it. So if you're drawing like a 50 by 50 shape and you have like a 4 pixel wide outline, it will actually stretch out to 52 and 48 since that outline is on the center. And we kind of get into that a little later. When you're drawing outlines, you like always have to account for that, and it gets a little annoying because you always have to like shrink everything a little bit, make it fit into the size, and that kind of stuff. The graphics class, I should note, it does not allow you to combine multiple shapes. So every time you're drawing a shape, it's basically one graphics call, draw rect, draw ellipse, but you can't say like add a star, a rectangle, and a circle, and then draw all of that at once kind of thing. And we'll get into that later. It's actually the path class. Cool. So example 2.2 from the folder, sweet, is drawing the simple shapes. And basically we just go through, and it's just an example of everything that it has to offer. So we get a nice little 80s looking kind of thing. That just has, in the background, we have a checkerboard. So if you just easily want to say, like, I just want, you know, 10 pixel wide checkers in dark gray and gray across my whole component, we can just do that with one call. So you don't have to manually go in and say, draw a rectangle here, and then move over and draw one here, move over again, and set the colors back and forth. And it manages this through rectangle lists, which is another JUCE class. And we kind of go over these where JUCE has some geometry-related classes like the rectangle, point, lines, that kind of stuff. Rectangle list is one of them where you can just add a bunch of rectangles and make a complex shape out of it. So if you add one and you have like rectangles that like stick out of the side or something, it basically just has all of those and it will coalesce them, and it'll know the full size that it takes to draw that, but you can pass it off to the graphics context to say like, I want to set red and like draw all of these rectangles at once. And this checkerboard one is even more simple example of that, where it's just a big list of tiny little gray and dark gray squares that it draws over and over again. So we move down. Size this window smaller. So that basically just this has the examples of it. We set our red color again, and we fill this little rectangle at 50-50, and it's 50-50 size. We fill an ellipse down here that's pale goldenrod color. We draw a line from our top left to the bottom right of the main component. So actually, if you take the little resizer here and move it around, this line will always be within, from here all the way down to here. It's just stretched diagonally across, since we're repainting all the time. And it's important to note that the graphics class is stateful, so that anytime you need to do stuff, you have to set all this up beforehand and then make the call. So here we are setting our color to red, then drawing the rectangle. So we're actually committing that rectangle to screen in the red color. You can't necessarily do things where it's like, I want to save some sort of shape and it has like all of these attributes like color and outline and font or anything like that. It's always the case where you have to set up the graphics state right then and then make a call. And your state is then preserved after that. So if we were to take out, this goldenrod color, rebuild, we basically just keep the same color until we actually call set color again. So yeah, then we can draw arrows, which there's a little arrow over here. I probably should put in a different color because it's hard to see. So there's nice things like that where if you just want to draw an arrow and you know how big you want the arrowhead to be and how long the arrow is and all that stuff, you can just make one call, pass off the line that you want, and then pass off the size information. And each of these, you basically just will read the documentation for each. Sometimes it gets into, like this draw arrow one is a little long because we don't have named arguments or anything in C++. So usually I end up like writing comments or like other kind of stuff or something like that. There are some where it's like, I think when you're drawing like rounded rectangles that have an outline, there's like 10 arguments or something to the function. So it's usually nice to set that up in like structs, just make like some custom structs and use those so you can actually keep the names in line with the function and know what each one is doing, or comment and stuff like that. Cool, so each one of these, as I said before, these first two are fill methods, so we're actually going to draw the full shape. Lines, you can't really fill a line, it's always going to be an outline. So that one's a draw call, draw line. Draw arrow is kind of the same way, it's technically not, it's filling that triangle, but down here we actually have the draw rectangle and draw ellipse calls, and those will be just drawing the outlines. So we draw this rectangle and it just draws it in a little thin outline. We draw an ellipse, it draws it with a 2 pixel wide outline. That's that last argument here. We could change it to something like 20 and we see this is larger. But I should note again that the bounds of it will actually be like this will be aligned to here. So the bottom of our rectangle and the sides of it will be within the outline. So you always have to account for like how thick is the outline and how much do I need to inset something if I want to keep it within this rectangle instead of, the actual one that we passed. Are there any questions about that, just drawing shapes and stuff like that?
So when you resize that, it hides that large circle.
Yeah, so same kind of thing. When we resize, it will only commit to screen what we actually have within our clipped rectangle, which could go all the way to 1-1 apparently. So yeah, and it actually will. One thing I should note is that it will still draw the full shape. It will not rasterize the full shape, but it will make the call. So if you have like some crazy complex shape that's going on over here, it being outside of the region that we're actually drawing to doesn't save you from all of that overhead of still making the shape and like sending it off and having it being having the path being traversed and all of that. But it will save you from the rasterize step, but not entirely. I think it still will go through and actually flatten that path out and figure out like here's the full shape that would be drawn to screen. It just doesn't get drawn to screen, so it's doing a lot of extra work for nothing.
If that question was getting at the question of fully resizable windows. What stuck in my mind with JUCE was some examples online where with about 3 lines of code for each of your children and grandchildren, and you can get your parent size, and you could resize everything inside to match your parent's size and have a, quote, truly resizable window, including text. If you just add these lines of code where the size of your object or size of your text is multiplied by this number, and this number is your current size over your parent size on X and Y. And so anyway, there were some examples of doing truly resizable windows like you'd expect in maybe a browser or something like that. But you have to add, 3 or 4 lines of code for each of your children to do that.
Exactly, yeah.
It can be done.
It ends up being, and there's a few ways to go about it too, but usually, like for example, the line, because it's always taking into account the bounds of like, we got to get our top left, which is always going to be 0, 0 in this case, to the bottom right, that will always work, but all the rest of these are hard-coded. So if we wanted to say like, okay, we know our main window is always 500 by 500, that's our default size. If we go lower than that, say it's 250, 250, we will want to take all the positions and the sizes of all of these other objects and shrink that down so they actually fit within that. There's some easier ways to do that we get into. I've handled this in both of those ways because all of our plugins allow resizing. Not by dragging, but there's like a little menu that you just go in and say smaller, and it'll just shrink it by 10, 20% or something like that. But yeah, it all comes down to whether or not you will have a static interface. Like I mentioned, a lot of those skeuomorphic plugins where it's just like, a big LA2A or something on the screen, you usually can't resize. Resizing doesn't always work very well in plugins. I'll just put that out there right now because I ran into a lot of annoying things where like sometimes it'll work completely fine. Like in quite a few dolls it works okay. Like Logic I've never had problems with. Pro Tools, it actually does work, but Pro Tools I've had weird things where like the sides of the window or that like toolbar that Pro Tools puts in the plugin window for you, like that'll just turn black or like disappear for some reason. So a lot of these dolls, I guess they set them up to not expect like resizable windows and stuff. And then of course you get into something like Reaper is probably the worst because they have the container window, and if you start moving that, like it doesn't actually resize anything. And if you do your own resizing, that container window just goes crazy on you every time. So usually when talking about plugins, it's pretty static unless you go that route of like, it's a menu option and you just shrink it by each size. And if you're doing that actually, then going through and just knowing your multiplier ahead of time is really easy because you can just say like, we shrunk it by half, so now it's only half the size, so we can just apply that to like all of our drawing operations with that number that we've already used for setting the size. But yeah, all of these examples, I think it gets into it a little bit later of relative sizes, and then later than that we go into like layouts, and you can do affine transforms, which will change the actual contents of the graphics context according to like a matrix. Does anyone else have questions about graphics context at a base level? I think we're going to get into the whole state setting thing next up. Cool. Switch back here. So as I mentioned, graphics context only lets you do simple shapes. To do more complex shapes, it boils down to using JUCE's path class, which is basically just points that all connect. So you can connect them via lines. They can be Bezier curves, like a cubic curve or quadratic, and that kind of stuff. And really, everything in JUCE boils down to using this. So when you call fill rect, it will actually construct a path object for you that is a rectangle, and then pass it along. So those simple calls basically abstract over that, where you want to draw a rectangle on the screen or an ellipse. Instead of making a path object, setting, adding an ellipse to it or adding a rectangle to it, and then passing it off to the graphics context, you can just do that all in one call. But if you need to actually get into more complex shapes, especially drawing like curves or anything like that, you have to use the path class itself and start setting that whole layout up of, here are my points, here's how they get connected, here are the control points for like my curves and stuff like that. And it's important to note it can be allocated outside of the graphics context, so you don't have to, you can just make a path class whenever, since it's not tied to using a graphics context or using an image or anything like that. So if you're doing like complex shapes, you can save a lot of work by just having a path like inside of your class or allocated off somewhere, set up the whole path beforehand, and then just when you're ready to draw it to the screen, just pass it off to the graphics context. So you're not like creating a path every time, creating this big list of points and like having to allocate those every single time. And the path class actually works a little bit like JUCE's array interface, where you can ensure that it has a set amount of storage. So you can say beforehand, like, I know I'm going to draw some crazy kind of FFT shape or something, and it's going to have like, 2,000 points or something. You can tell this path class that it should ensure enough size to hold 2,000 points, and then you can just start adding them instead of adding one, adding a couple more. The array suddenly realizes it's not big enough, then it has to like allocate more data. You run into that same thing again, where it's like you keep adding them in a loop, but the array doesn't know that you're actually wanting 2,000. So you can set up that 2,000 beforehand and then just run the loop and add them all in and keep that offline, so you don't have to keep doing all of that work every time you're repainting. The path also provides, I guess not provides, it's really just next to the path, is a path stroke type class, which really just has properties for defining how you want an outline to be drawn. So the outline size is one thing, but there's also the end cap style of, once it gets to the end point, is it stopping right there at the point? Is it drawing like a butt to the point where there's, it extends, the size of the outline that much further away? Or is it rounded, so it kind of rounds out at the point? And then there's the joint types of like, when there is a sharp curve or a sharp change in direction, basically, is it just going to be that sharp point? Will it be beveled off, so it will hit that, flatten out, and then go back down? Or will it be rounded, so when you draw it, it's just is a slight little rounding to give it nicer shape? And usually I end up using rounded on everything. It kind of just depends on what you need it for and what exactly you're drawing as to whether or not you have to deal with like the path stroke type stuff too often. So the next example, go back here. Complex paths, pretty much the same thing as before. We're just drawing shapes, but we make a path class at the start of our paint loop. I've included all the links basically that point to, like, if you're drawing a type of shape, like you want to draw a triangle, this is the exact method that is in the documentation for it. So we go through and basically just add those kind of shapes. So we have a triangle, a star, we draw our own little curve right here, and we actually use the path to draw the background as well. So our first use of the path is that we add this rectangle that's just this pink square, a little bit reduced, and we call fill path, but we have to clear the path after we use it because we will be adding more points to it. So if we were to not clear the path, which, just comment that out, you'll basically end up with not what you want. So it will actually still draw the outlines correctly because it knows where all the points are. So we still have a rectangle, we still have the lines, we still have the star and everything. But the fill of it, it doesn't quite know what to do with because you have points that are like inside of this shape. So is it supposed to draw like nothing in here, or does it draw here? In our case, we actually fill it twice because, yeah, I guess we're still calling fill. So it fills it once over with the pink, and then it goes over again and is like, okay, well, I have a rectangle all the way here and some shapes inside, so I'll just fill the whole rectangle with white. So we see everything in white, and then just only the outlines end up coming through since they don't overlap on top of each other. But those fills will mess it up if you don't clear the path. So I usually do that, like if I'm going to be drawing a bunch of shapes that do use the paths, I'll just make one path object at the top, so I can just always say, I'm using path, and I don't have to have a bunch of variable names to remember it. But anytime you start swapping around and changing shapes, you're going to have to clear out the points that you were already using, basically. So we clear it out, then we add a star. Here we go down, and we add the triangle by actually just doing our own line segments. So if you are going to go through and say, like, I want to draw some lines that, encompass this area or something, you have to start a subpath for that. And that's essentially what we're missing when we were not calling clear, going straight from the rectangle to other shapes. It will start the subpath for you, but it's going to all be within the same shape. So we start a subpath over here, and it's actually still part of the same path object as this star. But because it's started over here, we don't have to connect any lines. We don't have anything going on that's kind of weird like that. If you were to not start the subpath and you said, like, made a bunch of line 2 calls down here and you drew some triangle here, and then you said line 2 up to here, it would actually connect that all the way across. So you always have to start subpaths with where you want to start it at, draw your shape, and then close the subpath. And a good example of not closing the subpath is in this curve right here. We start our subpath at 200, 200, and right now we're using the quadratic curve, which just has one control point. So we have our starting path, and we have like some control point over here, and JUCE will do like a Bezier curve based on that control point. So it'll round this out according to that. But we don't actually close the subpath. And as you can see, the fill will actually go back and like figure out, okay, what was the path or what was the last point that I'm supposed to go back to? So the fill will go back and draw that. But if you don't close the subpath and you start outlining things, it will only outline from the points that you defined to the end points. So if you're not closing your subpath, you're going to have like an open outline like on this, as opposed to here where we closed it, the whole shape fills in and the whole outline draws. And obviously if you use any of the shape methods, it'll do the whole subpath thing for you automatically. So JUCE basically offers those two kind of Bezier curves. So we have the quadratic 2 method, which uses one control point, and our cubic 2 method uses 2. So we have one control point that's like pulling this shape out here and another one that's like pulling it out this way. So we can draw it through. And basically, you'll get into winding modes for the paths. and which is how it determines its fill shape. So here, like the default is if you're crossing over, we will fill it in this way, and once you cross over, it's going to go back over this way. And you basically just have to end up knowing, like, if you want this to work out correctly, you have to have your geometry correct for that, or you get into using winding modes, which determines basically just the algorithm of like how it figures out what is the filled in part of the shape versus what, you know, is everything else outside of that. So we call fill path to draw our shapes in white, and we have our path stroke type, which always has to take arguments in its constructors, if I remember correctly. And it just has the outline, and like I mentioned before, there's a joint style type that it has, which is either metered, curved, or beveled, and the end cap style, which is, as I said before, butt, square, or rounded. So yeah, it always has to have some sort of argument, so usually you're just constructing it with like the thickness, and then you can explicitly say like set joint style, or joint style is curved, set end style, or end style is rounded. You can change this to another end style. And I probably will need to make this a lot bigger to actually see those changes. Cool, so here we have the end style of butt. We go back to rounded. Over here, once it recompiles, you will see that this rounds out and it will extend past to the end point. So based on the size of your outline, using the square or the rounded end caps, let's go back to doing square, will extend past it. There we go. So here, our square will actually go past it, so it will not end exactly on that point, whereas the butt one will. Have curved joint styles. We can also use R-E-R-D. Metered, which basically you're just going to have sharp edges to each kind of sharp joint. And the other one was beveled, which will cut them off, basically. So when we have our beveled edges, it just chops off the points for the star. So you really don't have, like, overshoot. It's kind of like the butt end cap style, but just for joint paths. And you also see it works on the outside of the star and on the inside of the star as well, since we have the sharp joints going that way. Are there any questions about paths and all that kind of stuff? As your curves and outlines. Cool. Let's continue on. Two, fill types. This one's pretty straightforward. You just have these methods of set fill type and the more simple ones of set color, set gradient fill, or set tiled image fill. So you're either filling something in with one solid color, you're defining a color gradient, which is just a list of colors and 2 points that get mapped out, or an image which just gets tiled based on the size of the image. And on top of the fill type, you have the opacity of it. So once you set a fill, you can set the opacity just for that fill. So once you call graphics set opacity, say we set the color to red and then we call this with 0.5, it's essentially the same as if you just called set color with red, you know, with alpha of 0.5. So that's really if you're using like tiled images or like gradients and you want to actually just apply that, because otherwise you can just pass a color with an alpha. The more useful thing is, and JUCE uses this, as I mentioned before, begin transparency layer and end transparency layer. And JUCE uses this for a lot of its built-in components like sliders and stuff when the component is disabled. So it will actually just say, if we're not enabled, it'll begin some transparency layer, then draw everything, and then end it. So that the disabled component appears lighter and appears like it's not able to be clicked on because it's semi-transparent. And usually you'll see that a lot in more modern UIs, because JUCE kind of goes along with that aesthetic where it's like minimal, so we can just call like these layers of like just fade out the component a little bit to make it appear transparent and not clickable. This example is super short. Basically just have two rectangles. One of them we fill in with a sky blue color. The other one we set up a gradient for. Let me open this up real quick. So as I mentioned, the gradient is basically just a list of colors with 2 points. So it will, when you pass the gradient off to the graphics class, those 2 points have to be relative to where you're working with. So in our case, we use the second rectangle's top left and the bottom right to define where our gradient will start and end. And then we just go through and add the colors, Roy G. Biv, and we add it based on how many colors we're using, which is 6 since we're starting at an offset of 0. So we say red, orange, yellow, green, blue. All of those are split up into equal parts, and it will draw the gradient across the rectangle linearly. And if you want it to be the case where it's drawing those as like rings of color, you can change the radial property. So it will actually just figure out the size and then draw ellipses using the colors. So we can fade out a circle from red to yellow to orange, green, blue, violet. But yeah, we don't go over the image stuff in here because it's actually a bit later. But that would be the other one is you could say fill an image tile. Say you have like some tiny image that's like 50 by 50. It'll take the size of that and just figure out, okay, I need to place this many copies of the image, to fit this rectangle. But that is for a later example. And all of these basically map out to, there is the fill type class, which really just wraps around this. And this is how the graphics context, like when it's storing its state, it uses the fill type itself because the fill type associates like this is a solid color fill or this is a gradient fill and that kind of stuff. So it's not like keeping a copy of like, we have a color, we have a gradient, we have an image that might be there. It just has all of those saved in like a fill type and it'll just save the fill type itself. But yeah, usually you don't really have to use the fill type. You can use it if you want to transform it with an affine transform. So if you have an image or you have a gradient, you can apply some sort of transformation to the fill type and change it. But usually you're just working with the methods I mentioned before of like, set color, set gradient fill, or set tile and image fill. But yeah. Brings us to text. So in the most basic methods, you can just give JUCE a string, some sort of bounds, and some sort of justification setting, which they have their own class to define those. And it will draw the text on screen for you. And how it ends up doing that is all based around the font and the typeface that it's using. It will take those typefaces, figure out what the characters are that you're actually trying to draw, convert them to paths, and pass it all down to the low-level context to actually be rasterized. And it'll do all that layout, the kerning, and figure out the actual placement of each glyph within the text. So you don't really have to deal with that yourself. You can if you want, but I would not recommend it. It is not fun at all. But you should make sure that the area you're drawing to will be big enough to fit into the text. That'll be wide enough if you're just using draw text or draw fitted text and those kind of methods. There's also methods to draw multi-line text, so you can just say, like, I'm going to draw a couple lines, going outwards and down, and you will have to make sure that then it's wide enough to fit your minimum line width, and tall enough to fit how many lines you're actually storing based on that font height. So the font class basically just provides access to those typefaces that I mentioned. The typeface wraps around the operating system level of handling all of that. And every typeface, really, when you're using like OTF and TTF fonts and all that kind of stuff, are already basically vector graphics. So fonts are just the same kind of thing. You're just defining, these are the points, and I'm going to draw them out. But yeah, if you're making custom fonts, you will have to pass off like your own typeface pointer. So you're going to be using create system typeface for, which basically amounts to like within the producer, you can just add the font object or the font file itself to the project, and it will put it into binary data, which really all that is just it takes all of the bytes and writes them in a giant array and then puts that in your actual source code. So you can actually use that then to say like, oh, okay, I want to make a new font of my own custom type. When my application starts up, I'm going to have like a static typeface, and it's going to be created from, binary data, my font, OTF, and the pointer to that data and the size of the data. And the typeface will be created if it can read that font, obviously. And then you can actually just start using that with a font class. So you can make a font object if you have a typeface pointer, or if you just have the name of the font or anything else that JUCE can resolve the actual connection with. So usually it's using, in our plugins we do the custom font, so it's always a typeface, and we basically just have a bunch of static fonts that, like, if you want the regular font of, the Harrison font or whatever, or the bold font, you can just say like Harrison fonts regular, and it's a static object, so it'll always be there in your binary available to you. But if you're going to be if you're doing something like a code editor or something, which the producer offers, and you're going to be swapping out fonts, you'll have to use JUCE's classes for actually reading what fonts are installed on the system, and those will just be given to you as strings. And if you want to change fonts, you have to tell it the typeface name that you're trying to pick, and it'll go and resolve that and figure out what actual font file it has to read. Same thing with styles. If you have like some sort of font and it has some style name attached with it or something, you can change to that style by passing the style string, which is also available from the font class itself. But yeah, and it'll manage size. So when you have a font, you can like set the font height. You can adjust the kerning of it. You can set the typeface and style. You can say whether it's bold or italicized or underlined and all that. And once it's actually drawn to the screen is when all of that resolves, and JUCE will figure out what it needs to do to actually draw an underline or use the bolded version of the font to actually draw things. Laying out your own characters, as I said, don't do this. It's a nightmare. But if you absolutely have to for some reason, the easiest is probably going to be if you're doing some sort of like multi-font and color layout. Like say you have, and we actually do this in the example too, say you have some text that is like, we're drawing here and it's in a certain font, and then just in the middle of the sentence we switch to another font and switch to another color and a different style and everything. You can do that with the attributed string pretty easily because it just maps it all to methods where you're going to say, add some text, add it with this color, add it with this font, and it just saves that range of text using that information. And when it needs to actually get drawn to the screen, then the attributed string and the text layout classes handle that for you, where it's like, okay, we have this size area that we're working within, and our first range of text is at 12-point font, it's in a white color, it's not bold or anything. It'll draw that, moves on to the next range, figures out like the actual placement and everything. Laying out your own characters is possible. If you need to know how long your string is going to be, you can use get string width. So if you need to basically find out the area that you're working with after you already have your text and your size, instead of the other way around, then you can use getStringWidth and like say when you're drawing the text, I'm going to draw it with this width that definitely will encompass that. Do not use glyph arrangement. It is a nightmare. But if you absolutely have to, that's how we did in the Hack Audio UI library. There's like kind of the LaTeX style stuff where you can write math equations and it'll do like subscript and superscript and fractions and stuff, and that is how that was achieved with the glyph arrangement over a very long time. Cool, so text layout, basically just going through the basic text stuff. So we keep our bounds up at the top. We fill our background. Since we're drawing white text, we don't want it on a white background. We get the local bounds, and we're going to say we are going to take chunks of 25 pixels tall to draw each line of text for now. So it'll be the full width with just 25 height. And we draw our first one, white smoke, color, font size 24. We just draw some text. We can say hello world. We give it the bounds that we're working with, and we say centered left is our justification. And the justification class basically just offers, it's just essentially an enum of, left, centered left, top right, any kind of positioning that you want to do, justified, bottom, centered, all that kind of stuff. It's just within that class, and you just pass off these values so the graphics class knows how to do that layout. So each time we draw the text, we're going to translate the bounds a little bit so that we can just shift it downwards. That's part of the rectangle class. Here we draw, get my window back, JIT process crash, segmentation fault. That's not good. How that happened. So we draw some fitted text, which is going to be way too long. And we're only working within 25 tall and this long, and it's only going to be on one line. So it goes past the bounds, JUCE realizes that, and it draws in the little ellipses for us. It also squishes the text as well, so there's a few arguments to that. The first one is going to be the string. So basically here we just draw our full string, super long, verbose text. And a cool thing to note, because this is really handy, if you place string literals next to each other in C++, it'll just concatenate all them together, so you don't have to say, like, I'm making a string, and then I want to add to it with this line, and I want to add to it again, because otherwise this whole line would, like, go so far off your code editor, it would be hard to read. So we can just do that by saying, like, okay, we're just going to add all these, put a space at the end, it'll concatenate it for us. So we have one huge sentence, filled in the bounds, centered left. This second to last argument is how many lines we want it to have. And it's only going to be, the draw fitted text class method will let you do multi-line text, but only if you're inserting new lines into that text itself. And since we're not doing that, when these concatenate, it'll just take this and add it here. It doesn't actually put a new line, even though we have it down here. Because we don't have any new lines, we're only going to use one line anyway. And then the very last value is that horizontal scaling.
Well, if you did have a ASCII carriage return and ASCII line feed, what would it do?
It would...
I mean, embedded in the text.
Yeah, it would probably not show at all because it won't give you any hints if it goes vertically off, like it did with the ellipses on the right side. So it'll try and draw that lower. It actually... Oh, let's put one in there. I'm not sure if it keeps it to the bounds or not. Okay, what in the world happened? There we go. Okay, so it will not only stick to the bounds you're working with. And interestingly enough, it actually, and I don't use this very often. If I'm drawing multi-line text, I usually fit it out in a different way because trying to just use the draw fitted text method is a little clunky. But yeah, it actually drew, it fit all of it lengthwise for the first sentence, but it shifted all of it up, and then it tried to fit everything else like down here. So usually there are some things for like drawing multi-line text and setting out the bounds for that and making that a little easier, or using the text layout stuff is even easier than that. But yeah, if I'm working with multi-line text, I usually go for those methods. But when it's on one line, we can adjust whether or not it's actually going to squish down. So before we got to the word window, before our ellipses came up, but here we're going to say we do not want this to squish at all, so it's always going to be 100% full width for the characters. So hello world is going to be the same length as the original one because it still fits, and it will just write as much as it can until it runs out of room, and then it'll figure out how much room do I have left to at least put the ellipses in and let the user know the text doesn't fit. So moving down a little bit more. Here we use the multi-line text, and rather than writing it using new lines and stuff, this is just a quick example of C++ raw strings, which basically anything you write in between these delimiters, which will be R parentheses parentheses, R quote quote, then the parentheses, and then it ends with the parentheses and the quote quote. The entire thing, including new lines or anything, will be written in. So if you actually had like tab characters and stuff too, it'll just write all that in. And these quotes are really for like, you can say something in the middle of it, like if we're inserting Python code or something, you can put that in there, and some editors will actually pick up on that and then like do syntax highlighting within that raw string, which is pretty nice. I use this a lot for if you ever get into OpenGL stuff, when you're writing OpenGL shaders, I just put them as their own files, but they're within a raw string, and then I just hard include that file into my C code when I actually want to use the shader. So that way I can keep the file separate and not have to do like embedding or anything. I can just include it when I want to use it. And it's all in a raw string, but it still actually syntax highlights everything properly for me. So here we have hello world, and we have an implicit new line because we actually moved to a new line in the raw string. And we say this is some multi-line text, pretty cool. We draw it, and when you're drawing the multi-line text, instead of, go to the graphics class. If I can spell graphics correctly. So before we were passing bounds, like down here in this draw text method, you pass like, I have an X, Y, and a width and a height. That makes up my rectangle. And that's all fine, but in certain other cases, like this draw multi-line text, you give it a start X, and you actually give it a baseline Y. And that baseline is going to be the bottom of your text. So if you have like, hello world, actually what's a better example? I have a Y in this one. Like if we say pretty cool, the bottom of all of these characters up into the Y is the baseline. The Y extends past that, but you basically have to align it to say, here is my starting Y position with the height of the font that I'm using, and that's my baseline. So I actually don't use these quite often because it gets kind of annoying to format all that. So for here, it's like I wanted to draw this, and I had to get the Y of the bounds I was using, and then like get my font, and then give it a height. And then you basically just give it like how long do you want the maximum line width to be. So we could say this is something short, like 50, and it'll chop off some of our text. Without the comma though. Yeah, so with a line maximum line width of 50, we can only fit chunks of each word in, so it'll just like split it up and put them onto different lines. So
So if you're using the multi-line text and you really want it to be multi-line like in our first example, you have to figure out exactly how you're going to fit that on the screen. Otherwise, if you're using like a maximum line width, it can still work, it just depends on what you're using it for. But you'll just have to figure out like, okay, this is how much space I have allotted to draw this text. So we give this a big offset, we move it down 130, and the rest just basically shows we can get the font, we can make it bolded, we can get the font again, we can make it italicized, get the font, make it underlined, which it does not have a underlined method. There are certain ones like underlined where if you want that style, you have to actually pass the style flag. So we have to say font with style, underline, it'll draw our underlined text. And finally, we go over the attributed string stuff. So here's that example where in one draw call, we can draw text that's at a regular font, make it smaller, make it the regular size again, but then draw it in two different colors, all within one string. So each time we basically append some text to the attributed string, and it works a little bit like the graphics context, where whatever settings you're giving it once you start out, it will keep those settings until you actually change them. So here we draw the first line with 24-point font, and it's in a white color. It will keep the white color for the second line of text, but when we change the font, it'll actually change that. And then to get back to the red text with the original font, we have to go back to 24 and change the color. And then change the color again, and it keeps the 24 size font. And instead of passing it to the graphics class, it's the other way around, where you have to call draw method on the attributed string, and you give it the graphics class context and the bounds that you actually are working with. So it will go through, figure out the layout, and then make these draw calls like in a loop, basically, of, okay, we're going to draw like this line of text, then we shrink it down and draw it across here, then we change the colors, and we put those paths on screen.
What is the attribute string dot draw method? The second argument, bounds dot to float with no argument. What is the to float with no argument?
Right.
Doing?
So there's a little bit of a disconnect in JUCE's API right now, and actually they are changing this later. But certain methods, like before, we pass the bounds like to this draw text call, and it's all started with a integer rectangle. So the rectangle class is a C++ templated class, and when you have a rectangle that's an integer, if you need one that is a float, instead of having to do like let's see here. Instead of having to do like bounds, get x and like cast that to a float, and like that kind of stuff, JUCE basically just added a toFloat method of the rectangle class, so that no matter what the type is, whether it's an int or like uint8 or something, or even if it is float or double, it'll just return a rectangle of float type with all of its members casted to float. And that is basically used in all of the vector-oriented graphics methods. So in the text, usually it will just take an integer bounds and like map that across. But the attributed string will actually take a floating point rectangle, even though it is still working in the text with the text classes. So it ends up using like int bounds anyway. But there are certain cases like that. A better example is that all of the path classes take a floating point rectangle, because you can draw, path points anywhere on screen at like, they don't have to be on pixel boundaries, essentially. You could put a point that's at like 1.5 pixels wide. So the attributed string does the same thing, where if you're laying out that text, it doesn't have to be on integer boundaries. It can be like, 500.5 wide or something like that, and it'll figure out how it needs to stretch those paths out to like fit that.
Oh, so you said it's changing. Are they going to go to make everything float? Or?
That's what they want to do, and the reason is because everything in JUCE is already vector. I don't know if it was just nobody thought of it or something, but yeah, like everything.
Well, conceptually, a pixel's a pixel, so it's an integer.
Mhm.
But I mean, underneath that, everything's float. So
Exactly. So, at the very last step before rasterizing, switch back. So, as I mentioned before, JUCE offers affine transforms. Love that here too. So you can apply matrix transformations to most anything. Not every call will accept them, but a lot of places where you end up drawing things will let you add an additional transform. But you can also just add one straight to the graphics context itself. So if you want to say, rotate everything by 45 degrees or something, you can just add that to the graphics context, and then it'll draw everything rotated from that point on. That can get a little bit cumbersome if you want to if you're doing something like drawing an image and you only want the image rotated, that would be a little bit overkill, because once you add that transform to the graphics context, it's basically there until you reset the graphics context state. So, and that basically is what I mean when transforms can be stacked. Every time you're adding one to the graphics context itself, that's applied to the previous one from before. So if you rotate and then you say, okay, now set, add a context transform that is scaling, it'll be scaled and rotated. And it'll just keep stacking until you actually like reset the graphics state and go back to just a transform that has nothing applied. So the types that can take it, usually like paths and images, you can draw them when you make that like fill path call. I believe it actually will take an affine transform. Yeah, so there's an optional affine transform in a lot of calls, like filling paths, drawing images, that kind of stuff. But you can also actually just apply it to the path before you use it at all. So the path class has like a add transform method and stuff like that. So you can just say, take all of my points and transform them in this way. And then from that point on, the path is always transformed. If you just pass the path off to the graphics context and give it a transform as well, the original path is not modified, but it's still transformed. So once it's done drawing that, your path is still the same, but it was drawn to screen using a different transform. So you can just do that easily without having to say like, oh, well, I rotated the path and I want to draw it. Oh, but now I got to rotate it back if I'm using it somewhere else or something, and I want it to not be rotated. So a lot of the graphics methods will let you supply a transform with that and just easily say like, just this draw call, just rotate this thing. So swap back over. We just have a basic example of rotating. So, open up live build. Same kind of thing. We start out by actually setting the origin of the graphics context. So usually the origin just starts out at 0, 0, and it doesn't really change. It'll change with each component. So when you say like, okay, I have a child component that's in the middle of the screen, it'll clip the rectangle region to that child, but it also will move the origin for you and then move it back when it's done. But usually you don't have to move the origin around yourself, but we do it here just to demonstrate the whole stack of affine transform features. So we move it to 100, 100. So when we draw this rectangle that is at 0, 0, really we're starting out at 100, 100. Open this up. So we have a red rectangle here, and we say, okay, we're going to rotate the graphical context itself by pi by 7. And then we're going to draw the same rectangle again at 0, 0 with size 100, 100. And this is rotated about this way because the entire context is rotated at this point. So when you're actually drawing anything, your origin will still be here, but it's as if your bounds like were moved from here to like rotated. So everything is going to be rotated from that point on. So we draw a rectangle again, and it is rotated around. And then we move on to this violet rectangle, and what we do is we actually add a translation transform to the context. So we're going to say that we're moving the moving the graphics context as a whole by 100, 100. And what that ends up with is that we move this back down. So if we weren't rotated, we would be moving 100, 100. But we are rotated, so we're moving 100 this way and 100 this way. And then we draw another 100 by 100 square in violet right there. So every operation that you do is going to be stacked and applied to the entire context as a whole. So anything that you do from that point on is just, you always have to know that like, okay, it's going to be having rotations applied and translations, but it's only after you apply them. So we can draw this red rectangle without any transformation, only draw this with rotation, draw this with rotation and translation, and it just keeps stacking on from there. And then we use the a scaled transformation, so we scale it down by half each way. So when we draw it again, we're going to draw it that same origin, moved over, rotated and moved over 100, 100, but we're only drawing within half of the size that we were drawing before. So everything in the context will be shrinked after you apply that transformation. So we draw our rectangle again at 100, 100, but it's only going to show up as 50 by 50. And finally, we just take the last one and we shear it across. So we use a 300% shear for the x coordinate. So it'll just basically take all of that. It's as if you took all the x positions and just kind of. Okay, so I guess we left off right before the first example. So this will be in the third folder, first file. Switch over the laptop. So this one involves a little more stuff just because we have to get the image into there. But it's basically just drawing an image. So we have an image that we're going to keep inside of our demo component. Whoa, what in the world? Some weird color stuff going on there. Let me try unplugging this and plug it back in. That was very strange. Yeah, so we need to get the image and actually load it from disk in this case. So we use JUCE's built-in just file chooser component, which I included the documentation for here because there's quite a few things that it can do. But here we just give it a title to open an image. The default, it's just going to not have any folder or anything open. You basically can tell it like, do you want to open, the user's pictures directory or something like that. And our file wildcard allows for PNG files or JPEGs. So then we use the file chooser and we ask the user to browse for a single file to open. And if it returns true, it means that they actually picked the file. Otherwise, you can hit cancel and it just won't pick anything for you. And so the file chooser, we can get a result, and that just has one of the JUCE file objects, which is basically just a path on disk that you can call methods to like know whether it exists or read the contents of it and that kind of stuff. And to load a file from disk, we have to use this image cache class, which usually is used for like you can save a cache of images that it will keep it around as long as they're if it's being used frequently, it will keep it around. So, for example, if you are only calling or only creating an image object in your paint method, this you can set like the timeout to keep it around for like 5 seconds. So if you're repainting pretty often and you're not keeping like an image object alive for that time, like if it's only used in the repaint function, the image cache will just keep another image object so that reference count is still above 0, and it'll keep that actual data allocated for you. In this case, we use it to load the image from a file, and we assign our selected image, which is a member of our main component, as the result of that. So if it is a valid PNG or JPEG file and not corrupted, we should get an image in. If it can't be loaded, the image will not be valid. So here we check whether it actually loaded or not, so we can set the size according to that. So if it is valid, we're going to get the width and the height of the image and actually set our component size to that. Otherwise, we're just going to set it to 500. And if it's not valid, we will not be drawing it. Otherwise, we're just going to use this draw image at call, which you basically just give it the image and then give it position, and it will draw from that position the full bounds of the image, assuming it fits into your graphics context. So as soon as we hit play here, because it's in our constructor, the file chooser opens up. There we go. And we go in the top level of the repository, I put the JUCE logo in, so we can go and open that file up. And there it is on the screen. I like how they don't make the demo window big enough, apparently, but it does fit in the full bounds of the component. So yeah, you can load just images off disk like this. Like I mentioned before with fonts, you can actually just take an image and put it into your JUCE project, and it'll include it as binary data. So it will just write the full like array of bytes into the source code, and then you can just start using that array anywhere in your source code. So that would be about the same thing. I think the difference would be JUCE image cache get from memory, I believe. So you can load files from memory or from off of the disk, anything like that. So yeah, it'll be in the correct format, ARGB in this case. If you are actually writing out an image or reading in specific images, like in our case, it knew that it was a PNG and like handled all that for us. But if you actually want to write out images, let's see, what is that called? They have these format classes from image file format. So this will actually know, like, it has to implement what kind of file extension that it might have. Like in the case of JPEG, it can be JPEG with an E or JPG kind of thing. I think even JPEG 2000 files are covered under that. So it has to have the format name, and it will know the extension that it might have, and then it will actually, you can decode the file once you load it into memory and pass it off to one of these. So if you have a PNG file and it's properly formatted, you can pass it to a PNG image format, and it will be able to decode the image and actually get you an image from the PNG file. But yeah, if you had it the other way around, where you're starting from an image and you're already drawing something and you want to save it out as a PNG, it'd be basically this of you give it an output stream that it has to write to, and it will tell you whether or not it successfully wrote that. So it could be an output stream in memory, it could be a file somewhere on the user's computer or something. But yeah, usually you don't end up writing files out, or especially images in JUCE. I mean, it's all audio software mostly. But I've done that for some stuff if I like want to just save the actual graphics out. We used it a lot actually for like the screenshot stuff I mentioned with the SVG. If we wanted like image files, I put in a little thing in the settings menu during debug builds that you can just like take the whole contents of the window and like dump it out to a PNG and then just send it off to the marketing guys or whatever. So that stuff is sometimes useful when it's like, oh, I don't want to sit there and like take screenshots and like crop it into the right area and stuff like that. Yeah, obviously if you're making like an image editor or something, that would be a very crucial part of your application. Cool. So that gets us into image buffers. As noted in the last example, the image object itself was a part of the, it was a member of the demo class. So that's going to be kept around whether we're drawing to the screen currently or not. And this can be useful if you are doing more complex graphics that you only want to update every so often, or something that you might need to fill out these graphics beforehand and you draw it to the screen at some point later. You basically can just keep the image buffer around and draw into it whenever you want by making a graphics context using it. And then later on, when you actually want to show it to the user in your paint method, you can just pass it off to the paint graphics context and draw it to screen. So it's useful for like back buffers and stuff like that. Like I mentioned, you can give a graphics context an image to draw to screen, but if you do it the other way around, you can make a graphics context by giving it an image. So it'll like use that as the backing store basically, and anything you draw into it will draw into there. So that gets into the second example. Is pretty short. It's just a quick demo of that. Examples. Buffers. So basically, we have an image buffer that we keep around. We keep this image buffer as a member of the demo component again, but we create it in the constructor and we draw into it in the constructor. So here, when you create an image, if you're creating one with an actual size and a format, it will be a valid image and JUCE will allocate that data for you on the heap. So we make an image ARGB, so we have 32-bit and supports transparency. We're going to make it 500 by 500 because our component is also that size. And then you can tell JUCE whether or not it needs to clear all the contents of that. So if you allocate this data and you don't clear it and you start drawing it to screen without drawing anything over top of that, it'll just be like random garbage, basically. Probably just like noise all over the place or something weird. But we are going to be filling the entire contents. So just for the sake of like not going through and clearing the whole thing, we just don't clear it. Usually if you're doing like a transparent image that's going to be over top of something, you'll want to clear it just in case. So here we can make a graphics context by actually passing it the image and going into blue again for whatever reason. I really hope that is the display and not my graphics card. So yeah, we make this graphics context based off our buffer, and then we can just draw right inside of this constructor, basically. So we're not inside of the paint method. We can just start drawing into the image. We fill all of it with sky blue, set the color to white, set a font, and then draw hello world again. This time using the clip bounds, which will basically be that 0, 0, 500. And by the time we actually paint it, the buffer is valid because we set all this up in the constructor to actually have a block of data associated with it, and we drew into it. So we see hello world anytime we're repainting because it was created once and will always be there. If we
were to set a time or something inside for this string, this will not be updated, and anytime you're repainting, you would have to go back in and like update your actual image itself before you start drawing it. So it kind of comes down to what you're trying to use it for, on how you set up the structure of like, when do I need to like update my, my backing buffer, my off-screen image. Do I do it like every time I'm painting would kind of be overkill, but like at that point you could just draw it. But is it every time, like every so often when something changes, we'll just update it, or is it only if the user is interacting with something? But that really all depends on the use case, basically. But it's a great way like to just draw something once, especially, and if it's something complex, then you don't have to keep repainting it all the time. So you can save a lot of CPU usage that way, of just draw it once and just keep the image around, and then just draw it whenever you need to like show that graphic again. The only thing is that you are kind of trading off memory usage for CPU usage. So it's kind of a balancing act of like, is this more efficient to do it this way versus not? Or like, am I allocating too much memory by keeping all these images around when I don't really need them? Because JUCE will also have, it has another buffer basically that is the contents of your window. So you kind of have like two copies of the image saved at once, so to speak.
Could you talk a little bit in this example, when you go to have paint and we have the reference to the graphics G, is that using the one that we have declared up above? And how does that
No.
work if we don't have, in other examples, when we haven't created graphics G, that's part of the project, or?
Yeah, so in this case, G I just use as the placeholder for the context all the time. So I used it here too, but this could be anything like context and stuff like that. But it's the graphics context will only be local to this function. So this can be stack allocated as well, to where you make a graphics context somewhere in the function. When the function exits, that context is out of scope, and then it just like commits everything it did to that image and like stops. You basically can't write into the image anymore unless you have another context open for that. So we use this first context here only within the constructor of our demo component, and then when it gets to here, we basically don't have this context anymore, and we're not drawing anything into our image buffer anymore. So this context is what is passed in, and this is the it's by reference because of it's going to have all the state and everything that JUCE has already been using for the previous components that it's painted. Basically, that whole component loop that it's going through to paint everything. It'll pass you a reference to the context it's using, but here we can just use our buffer because we already drew into it before, and we take the current context that we're actually painting with, and we tell it to draw this image, and we give it the buffer, and it takes all the pixels and basically just copies all of them into there at that correct position. But yeah, this one is the one that you will not have direct control over exactly on what kind of image like backing that it's actually using. JUCE will just allocate that in some way, likely for your whole window size, and draw into that by just going through that component loop, doing the reduce clip region stuff, painting each component, and like moving on, and then finally just committing all that and like refreshing the window contents with that image data. Yeah, that's the basic of the buffers, and the way that you actually start applying that is when you get into caching for components and stuff like that. So as I mentioned, you can cache complex graphics if you have something that it's really expensive to draw and you only want to do it every so often. But if those graphics that you're actually using are from a component,
The component class offers you an API to easily handle caching that and like saving it to an off-screen buffer and only updating it every so often. The most basic part of that is using set buffered to image, which will just turn on a flag that makes an image behind the scenes for you, and anytime that you call repaint on the component, it'll refresh that image. If you call repaint only with like a specific rectangle, say like 50 by 50, it'll just go to that first 50 by 50 and update the components, and then redraw the image, basically. But it doesn't have to invalidate that backing buffer all the time if you don't need it to. So it's kind of an easy way to do the caching for a component by just using the repaint interface. So when you call repaint, it refreshes. And if you want to use just a smaller region, it'll know how to invalidate that for you and do all that. As I said before, it's useful when the painting overhead costs more than saving, creating an image on the heap and writing to it, and then like going back and getting that data and like writing it over again into the context. Because if you do certain things, like if you're repainting a lot and you turn on like set buffered to image for the component that's being repainted a lot, you will see your CPU jump up probably like twice as much or more, just because it's now so much heavier to have to go and save all that data, draw into all of it because you keep repainting, and then like pass off that image to the graphics context that will then go and draw it on screen. So it's useful for things that are complex to draw but don't need to be updated very often. And one way that you can do that using custom behavior is with that cached component class. So this basically, and I think I mentioned it before, it's one of the things that JUCE will, you can set a cached component image and it will own that object basically. But under the hood, when you use like set buffered to image, it's just calling set cached component image with like a simple wrapper that just invalidates an image or doesn't. You can do your own behavior by using this, and basically all it is just a couple of virtual functions. One of them is to paint the contents on the screen. Two other ones are to invalidate regions of your image cache. So you can invalidate all, which is if the user repaints your entire component, or you can just invalidate a certain area of it. And then when the component is being deleted, if you need to release any resources, it will call release resources for you, and you can delete extra buffers or whatever you had allocated, basically. But yeah, and this is a good example of where this is actually used is in JUCE's OpenGL implementation. They used cached component image to handle the textures. So each component is actually drawn using like textures in OpenGL, which is basically the same as the image class. You just have some pixel data stored somewhere else, and you're just going to reuse it and draw it in this area. But to actually go in and like update the texture using the OpenGL API, they wrap that through a cached component image. So anytime you call repaint on that, it'll mark it, and like it will know to go and like use the OpenGL API to actually go update some textures. And when it paints it, then it uses the OpenGL API to actually get that onto the screen using OpenGL textures. But that's one use case for it that's pretty advanced. Usually if you're just like buffering something and you just want to like have it save the contents and not repaint it all the time, that set buffered to image call is pretty much enough. But this is useful if you want to like step in, basically if you want to insert yourself into the painting loop, because this will be called, let me actually go to this component. Cool. So basically, if you have a cached component image, this is the repaint that's going to happen on the JUCE side that will go in and make a context and like repaint your whole component for you. If you have a cached component and you're invalidating your cache, it will. Oh, sorry. This is actually the calling repaint. If you're calling repaint, it will do this, where it will invalidate all or sections of the cached image. But yeah, if you have an image, basically, instead of calling paint entire component, it will just go to your cached component and ask to draw the whole contents. So at that point, you basically control that painting hierarchy of how everything gets drawn inside of that component. So you could even do different stuff than just calling. The default would be to just, in your cached image itself, like you are painting the whole component, but you could also just set something and override it and change how things are being painted and like break the hierarchy and that kind of stuff. But that really gets into whether or not you need, like, sometimes I've run into weird graphical stuff where I'm like, oh, I want to do, this certain thing, kind of like that OpenGL thing, where it's like I need this to actually behave differently, and not just rely on JUCE's like going through each component, making the paint calls. So sometimes I'll use this for those kind of weird edge cases. So yeah, I think this covers. Yeah. Go back to. The last example from the image folder. So here it's kind of similar to the early on one where we had our main component and the component inside was being repainted, and you could see each one of them repainting at a time. Here basically we have one of our square components again, and it does a random color, and when you click on it, it repaints. And we added buttons in to either trigger a repaint for the parent, and to actually enable the cache for the squares. So when you click on this enable cache button, it will toggle on or off whether or not the square is like buffering its contents or isn't. When you click on repaint parent, it'll repaint the whole parent. And in our parent, all we do is really just write the current time up at the top. So we can know things are changing. So we trigger repaints. We see the time change, and we see the child square also repainting. And if we click just on the child, it will just repaint itself, but the parent isn't changing at all. Now, if we enable the cache just for the child, we can cause a repaint directly on the child still. But if the parent is calling repaint, you're not telling the child that it needs to be updated. So we can repaint the whole parent, but the child component will not change. It will just keep that same image as long as it isn't having repaint called on itself. So the parent's free to like update all this stuff, and it's a little more efficient because we don't have to repaint the middle component anymore. Now for simple stuff, I mean, it's probably more overhead to actually just use the cache, but once you're doing like really complex graphics and like you need to update large chunks of the screen, it will save you a lot of CPU usage to cache what you can, basically. Especially combined with like setting things opaque and caching their graphics if they don't need to be updated. It'll make it really cheap that like JUCE just will know, okay, I can just reuse this image data that I already have, and I don't have to go and like do all these paths again and like rasterize everything and go through all that expensive setup. So yeah, this main square will not repaint until you force it to by clicking directly on it. Are there any questions about images or
the caching systems and stuff. That takes us to JUCE's look and feel class. This basically is going to be not the way, but one way of how you can theme your application. So it provides you like UI customization through this interface. And all the look and feel class really is just a struct that it can hold some colors, like you can set a color specifically on a look and feel. But it also subclasses like every single built-in widget has some look and feel methods, and it subclasses all of those. So if you were to go into like the header file for JUCE's slider class, you'll see somewhere within there's a struct called look and feel methods, and all it is just a bunch of virtual methods that say like draw the slider background, draw the slider thumb, you know, give me the font that I'm using for the slider. And so that's how it composes the API for the actual look and feel class is just overriding all of these methods. And that allows you then to subclass look and feel and start overriding and providing different painting behavior based on, you know, whatever kind of theme you want to make. So the two important things with that are obviously the look and feel methods that are available in all the JUCE widgets. But there's also nearly every component. I think there's a few exceptions, like the JUCE base button I don't think has any of these. It does not have color ID enumerators, and basically they're all just unique integer values that are used to associate a color or a specific color that's going to be used with a component. So in the case of like the slider, when you go to the slider class reference, there will be a look and feel methods here. And it has stuff like drawing the linear slider, drawing a linear slider background, drawing the thumb for that, slider thumb radius, you know, drawing rotary sliders, all kinds of stuff that allows you to customize how that slider is being drawn, and even some stuff on how it's like being laid out, like the slider layout for where the text box is positioned and where the slider itself is positioned. Or if it's, you know, making buttons for like the increment decrement slider, you can actually just override this and make your own kind of button subclass that you're using. The same thing with the slider's text box here. And then it provides this color ID enum. So it's basically just a bunch of unique values to figure. You don't really need to know what these are, but if you're making your own custom color ID values that you want to use, you kind of have to look through all the documentation and just figure out, I'm going to start at this number and count up, because they don't list these. They didn't reserve any particular numbers, like they didn't say, you know, we're going to start every ID with like FF and then some number after that. But usually if you're using, they start at low numbers, so if you're using a high enough number, it'll always be offset. But they define things like, you know, slider has a background color ID, and in the look and feel, in JUCE's look and feel, definitely they go through and they check for the component, does the component have the slider background color ID set in its properties? And if it does, it'll take that color and actually use it. I'm going to set color here. So all components and look and feels basically have set color, remove color, is color specified. In the case of components, it actually maps to their properties, but it uses like a function to just transform what the name of the property is. So like if you set the color given some ID of like ABCDEF or something, the actual property name it'll save is like JCC something underscore, and then the actual like hex representation of that number. So you can accidentally start messing up the colors if you say like JUCE, you know, component, get the properties and clear all of them. All of your colors are also gone. So it's important to remember that, because they don't
note that necessarily here. But if you set a color, you can then find the color again, and it will give you back the actual color that you set for that. So, for example, you can set like the background color ID of a slider to be red, and just the background part, when it goes to look for that background color, it'll find red and start drawing that. But the track color and all the other stuff will be left to the defaults. And those defaults are usually defined in the look and feel itself. So if you call find color on a component and it doesn't find it there, find color you can specify to actually look in the parent component. So it can be like an inheritance kind of thing. That's off by default. But if it finds the color in a specific look and feel set for the component, it will use that color. So the order kind of goes, it searches through its own properties, looks for the color. If it doesn't have it, but you set inherit from parent to true, it will go, first it'll actually look in the look and feel if you set a custom one for that component. And if it finds it there, it'll use it. If it doesn't find it there, it will go to the parent and see if it uses it. And if it doesn't find that, it'll just fall back on like get, whatever look and feel I'm using and see if the color is there. And if it's not there, you will end up with just transparent black, basically. So nothing will be shown. So example 4.1 just kind of goes over the basics of that. Open up the demo first. Basically, we just have a few components: label, slider, text box, combo box. And each version of JUCE, they make a new look and feel, and it's basically the theming for that version of JUCE, which is usually what is used in the producer and stuff like that. So version 1 is like super old. I think they even say the years on here too. So yeah, everything derives from look and feel to actually get the versions. So yeah, 2002 to 2007 was look and feel version 1 kind of thing. So this is the default. If we go in and we pick something from the combo box, it sets the version basically. So this is their super old style. Some buttons and sliders. And then they kind of got into the Windows XP phase. It's almost like Mac or something. It's a very strange change. And then version 4 is what we already saw. That's the current one. But the demo code basically is just a lot of setup to like, okay, we got to put this label and the slider and all that stuff on screen. So we set the properties like that. And for the label, we're forcing it to a color because there was some weirdness if that wasn't in there. I don't think they were setting these colors in some of the older look and feels, so you had like white on white text and stuff that was unreadable. We set up our slider, all that, buttons. Okay, then we go, so for each option that you can choose for the combo box, we just basically set the look and feel to one of the look and feels that we kept in the member class. So look and feel 1 is an instance of look and feel version 1, 2 is an instance of version 2, and we basically just set those whenever the combo box changes. Is everyone familiar with C++ lambdas as well? This was the syntax I was using basically. JUCE, instead of having to use like the listener classes, which I think you guys use in class, right? So instead of like slider listener and slider value change, like overriding all that stuff, they did add members to each widget, or most of them usually, that are basically, it will end up like this. There's like a standard function that returns void and it takes nothing, and it's combo box unchanged. So you'll see something like that, like in the actual declaration of the combo box, and on change, like these kind of standard functions that they use, you can just assign to any function or lambda or anything basically that matches that function signature. So if it's a void returning function that doesn't take any arguments, that can be called by the combo box whenever it changes. So it's super useful for this, where it's like, I don't want to make, a combo box listener and override that and like put all this extra code in there. I just want to say, when the combo box changes, I want to do this function. So the C++ lambda syntax, I guess there's not a whole lot to it, but you probably want to read the docs online. But it's formatted basically. This is itself a lambda that prints hello world. And it will be assigned to like an object. So you could say like, I have some lambda or some standard function called my function, and use this lambda. And all it really does under the hood is just the compiler will put this function somewhere in your code, and then use my function as a function pointer to know where that function actually resides. So it's really nice because it lets you do a lot of like scoping stuff a lot more easily, and just makes it a lot less verbose to write things out. Like here we can just say hello world, and we can call my function as if it were a regular function, and that kind of thing. This combo box on change, it makes it really easy for that, because we can just say, anytime this changes, we're going to do this. When it comes to lambdas, though, what's super nice is that you can capture certain variables in them. So that is what the square brackets represent in the lambda. So in this case, we're actually capturing this pointer, which will be pointing to our demo component. And because this is like always implicit in methods and stuff, you don't always have to use it, or you don't have to write it out when you're actually making use of it. So because we capture this, everything that this has is visible and available to the function, as long as this is a real valid pointer. So in our case, we're technically grabbing this combo box and getting the selected ID. And when we want to set the look and feel, it's technically just doing, this set look and feel. So it makes it really nice because instead of having to, like if we had a listener, and especially if the listener was its own like separate class, not part of our main component, you'd have to start like passing, this class has to know about that class, and they all have to have pointers back and forth to each other and all this crazy stuff. But if you can capture things, it makes it so much easier. Like, for example, you can capture by reference as well. So if we want to capture the text button by reference, instead of this, none of this will compile because this pointer is gone. But we could say like text button and like just start doing anything with it. So you don't have to have like a separate class that's like a listener of the combo box, and you don't have to like give that listener references over to other things you want to use. It makes it a lot easier to just be able to go in and say like, look, I just want to write a function and it has access to this text button, and I want to do whatever I want with the text button. So that stuff's really useful when you get into callbacks and like doing actions with components, to just be able to say, anytime this combo box changes, there's only one thing that's going to happen, and that's we're going to go in and we're going to set the look and feel, and that's all you have to do is just write the function for it, basically. The arrow pointer stuff is basically syntax for declaring the return type of a lambda. So I always just be explicit with things. So in this case, we're explicitly saying this returns nothing, returns void, but you can leave it out if you want to. But yeah, we basically do that. I don't think there's any other actions in this one. So yeah, we set the look and feel based on the combo box. Look and feel 3, if you noticed, when we use that, it crashed. Segmentation fault. we go. When we go to the third look and feel, the button is red. And that's because we're using the color IDs that I mentioned before. But we're actually setting it for the look and feel version 3 instance. So here we set the color using text button color ID, which is the default color when the button is not on or pressed. And we set it to the red color. So any button like this one here that is instantiated and has that look and feel set for it will draw in red, unless it has its own color set for it as well. So we could override that by saying, you know, our text button, I think it's called, we're going to set the color, button color for that to blue or something. And once this rebuilds, it's blue, but it's blue all the time is the thing now. So every look and feel will immediately see this text button has a custom color set for it, so let's use that. But it will be blue everywhere. So it'll be blue in the third look and feel, fourth one, first one, all that stuff. This one I don't know actually. Maybe it's not using it. Considering that's from 2002, I would not be surprised. But yeah, and that goes kind of the other way around, where if we were to use version 3 and made like 50 buttons on screen, every single one of them will be red unless other, you know, specified elsewise. So it'll always go back to the look and feel class if you're trying to find a color, and if that component doesn't have that color set already. I think that is it for this, but there is one particular thing, and let me go back to JUCE's JUCE. Is that when you set a look and feel, you will have to, you know what, it's going to be in. When you set a look and feel, basically you just have to unset it at the end of your component's lifetime. So in our case, we have okay. So if we did not unset our look and feel, we will basically hit this assertion, which is saying you're trying to delete a look and feel while an object is still using it. So when you delete a component, it sounds like it's the wrong way around or something. When you delete a component, it does not decrement that reference count. So the look and feel still thinks like, oh, there's something that is like trying to use me, basically, and so it's gonna yell at you. It'll still work fine actually. Nothing should go wrong because the component itself is already gone at this point. But the look and feel thinks that like, oh, something is still pointing to me. I have to assert because, you know, this reference that you're using is not going to be valid anymore. So anytime you set a look and feel explicitly, it's important to make sure you set it to null pointer at the end of whatever you're doing. And this also applies for the default look and feel. So there's always like a static look and feel hanging around that you can use. And that in JUCE, it's usually going to be whatever the most current version is. So in our case, it's the look and feel version 4 is the default look and feel. But you could set it to your own and say, like, I'm going to use my own custom look and feel, and I'll just set it to the default, and then I don't have to set it for any components. At the end of your application's lifetime, you will still want to do this, or it will just assert at you every time you run your app, which is kind of annoying because it doesn't really, it's not really a problem. I think it's just backwards or something then. But it's just an important thing to remember at least. Okay, next thing is basically just a quick overview of custom look and feels. So like I mentioned, you'll want to derive a look and feel class, but you'll want to derive one of the subclasses because they already implement a lot of the virtual methods. Lots and lots of the methods are marked like pure virtual. So if you don't actually make one of those in your subclass, your program will not compile. So look and feel version 1 up to look and feel version 4 mostly implement, I think, all of them. So they're all safe to use to just like subclass, look and feel version 4. Everything will start looking like the default look and feel at first. But then you can branch off from that and say, okay, I'm going to make my slider look different. Okay, now I'm going to make the text button, customize that a little bit. But if there's anything that wasn't implemented, it'll just look like the default style, and it won't, it'll still compile, and you won't have any weirdness. And if you're doing that, you can also just store whatever you want kind of in the look and feel. Like if you're using custom fonts, you can store them in the look and feel, or you could do, like I mentioned before, just use static storage for the font objects. We used some extra stuff in our look and feel that we made that handles like our default background drawing because we support 2 themes. So when you switch themes, it'll actually, we save the theme name in the look and feel, and then we also save that in the save data for the plugin. And that theme basically just determines, what color palette are we using and what kind of background are we going to draw. But it doesn't even switch out painting. It's really just colors at that point. But you can do all that kind of stuff if you make a subclass. You can just use all that because usually any of that custom data will be used within the look and feel, and like the components don't have to know about it. So you don't have to like say, oh, I have this, I can call get look and feel on my component, but it's a look and feel type. It's not like, my custom look and feel type. You don't have to like cast and stuff because the component usually doesn't need to know about the look and feel. It can just call the painting methods that it really needs to paint itself. But this does get into some weirdness when you start using subclasses. So for instance, a good one is if you subclass JUCE's base button class, because I think it provides the look and feels, but it doesn't actually implement them. So when it paints itself, it doesn't even do anything. It has look and feel, so it has methods for like draw a text button, draw a button background, draw a toggle button, that kind of stuff, but that's actually implemented by the text button, toggle button, and other classes. So it gets kind of tricky if it's like I have these subclasses of JUCE widgets, but I want to use them with my look and feel, but like, I added some fields to the slider. Now it has some other kind of data member, and I want to be able to access that from my look and feel. The easy way without having to typecast that, which typecasting isn't really that bad, but it just does rely on like, I have to cast this to, my slider class and then make sure that that actually was what it was and doesn't return null pointer. Instead of doing all that, you can just use the properties map from before. So if it has, a property of like, my custom slider thumb. So the very last part of the workshop today is going to be about layout. So taking everything we had with making components, making custom graphics and everything, how do we actually get them on the screen, and how do we actually lay them out and make everything easy so we can make more complex hierarchies and interfaces? The simple way is to literally just go in and write everything by hand. So you have 2 options with that, which is absolute positioning, as we've usually been doing with set bounds and calling some sizes on it and stuff. But you can also use relative positioning. But as we mentioned before, you have to do this after adding all the children to the parent, and then you do have to do all the calculations yourself. So if you want to like split it up into thirds or something off of a chunk of the parent, you have to get that chunk and then split it up into thirds and then call each one with the correct percentage for the relative positioning. Usually you would be doing this in your resized method so that if you need it, at least, your component, when you are resizing your main window and stuff, the children can actually
have all of their bounds updated too, and everything will be more dynamic. But it's usually pretty hard to maintain. It's usually not too bad to read, but it's like you look at it and you don't really know where everything's going to be if there's a lot of elements until you actually like throw it up on screen and see what where everything goes. It definitely is hard to maintain because when you start changing things, your commits basically mean nothing. Of like moved to the left, like reordered the layout, and you can't actually see what changed because it's all just like 100 numbers of random positions and sizes. And it makes resizable and especially like dynamic applications a lot more difficult. Handle it that way. It's also pretty strongly tied to the components, so you have to go in and say, child 1, the slider like goes specifically right here, and any calculations relating to that are all just tied to that. So the very first example is just super, super basic. Kind of going back to what we already had in the early demos of just, we have some squares. The first one we position absolutely, so it's going to be 100 by 100.
Lost the video.
No, it keeps turning blue. Oh, now it's really messed up. I don't know if I should be worried or let's try this one more time. Give me the full screen. There we go. So yeah, the first one we could say, it's going to be at 100 now, and it will move over. This other one, we set it relative. So we actually go in the relative x position is going to be 0, so it always starts out just at the left edge. We're going to use relative bounds for the height. So we're actually going to take the height of the red square, which starts at 0 and goes down to its height. That is going to be offset by our height, so we can just always make it at the bottom of the red square using this set bounds relative call. It will always be 100% of the width, so this wide, and it'll be 33% of the height. So if we grab this and start moving it around, we can see that it changes. So the edge here, let me actually make this like 90 or something, so it's a little more clear. So if we make that 75%, the right edge moves along with our main component, and so does the bottom edge as well. But you basically have to say, okay, I'm going to go in and still hand calculate like every split. I want this to be offset by a fifth, and it's a fifth wide, and then the next one's offset by 2/5, and it's a fifth wide, and the next one's offset by 3/5, and it's a fifth wide. Like, you end up having to do a lot of the calculations still and a lot of the boilerplate really of just getting everything into the right place, even if you're just doing something like simple, like saying, I'm going to split this component into, 5 sections, and each one is going to have that much space. So that's the most basic way, and it's what we've already been doing. The step up from that is rectangle slicing, which is what JUCE calls it, basically. It relies on, I didn't even write it in here, but let me go over to how do I always have updates in Firefox? I don't know, like it somehow updates every 5 minutes or something. Like you can't possibly be pushing that much. JUCE rectangle. So the rectangle offers classes that will mutate and return a section of a rectangle. Or I guess, basically, you can call this method on a rectangle to chop off a section from it. It'll chop off that section of the rectangle and then return the section that it chopped off. So they are the remove from methods, which is going to be top, left, right, or bottom. So you can say, I'm going to split this screen up into halves. I'll remove, for my header, I'll remove from the top of my full bounds, 50, and then the whole thing's 100 tall, so I'll then just set the bounds for the other one, and it'll be 50 because we already took off 50. So they are, I should say, a lot easier. They're not slightly easier. They're way more easier than absolute layouts, and even more easier to deal with than the relative positioning stuff. It still kind of requires you, though, to figure out what you need ahead of time of, like, okay, I'm going to make my UI, like, I'll just decide on some random window size, and then I'll start chopping up the bounds of it and, like, set everything. Which is kind of what we do at work, where it's a little bit of the chicken and egg thing of, like, well, we know the sliders are usually this big and that, so we'll just, like, set the size here and then start grabbing sections and applying the bounds to those child components. And it's easy with a low number of components. That should say per component, because if you have tons of things on screen, but they're all children of the same parent, that is going to be one long resize method of just chopping up, like, all the little sections where they're supposed to go and doing all that. But if you split it up into sections where it's like, we have a header component, and the header has a bunch of buttons and some other stuff in it, that's easy, because then you just set the header, say, like, hey, the header's going to have, 100 off the top, and in the header resize, then you can just say, okay, no matter what we get, here's what our layout's going to be like. It's not very useful if components are kind of floating around or not easily in line with things, but I don't think that's ever really that easy to work in anyway, unless you just go in and hand position it. So in our case, like, our de-esser, like, some of the knobs, like, we have a graph and, like, a threshold and input meter and stuff, but then there's a section underneath where it's like things are just kind of there and they're not aligned to the grid or anything specifically. So it's a little bit of, like, okay, we're going to chop off this much, but then we're going to, like, shift it over a little bit and, like, kind of reduce it and just, like, get it to actually fit where we want it to be. And you see that a lot with, like, if you're doing skeuomorphic stuff where it's like things were just kind of in there and that's how, like, the real thing looked, or that's not really aligned to a grid, or, like, things are just kind of wherever. Then this can be kind of hard to use, and you may just still end up with a little bit of the whole, like, trying to work with an absolute positioning system anyway. So the second example basically just goes through creating one of those layouts. So we have our square components again, red, blue, green, yellow, violet. We have a 500 by 500 window. And what we do, this is usually how it's going to be set up, is you're going to want to get the local bounds for your parent component. So that'll give you the size, but with a 0, 0 position, because we're working relative to the parent. And what we can do is then just chop off sections. There's also an additional padding, so if you turn this on to 1, we can use a padding of 5 pixels or a padding of 1 otherwise. So each time we want to set the bounds, we're going to just pick wherever we want it to be. So the red square, we're going to set the bounds by removing 25 from the top and taking that result, that 25 we chopped off, and we're going to reduce it by however much padding we want. So by default, it's going to be 1, so it's just going to shrink it a little bit down on each side. If it was more, then it would shrink it down and it'd be past, it'd be smaller than 25. Probably smaller than 20. And then we basically just go through each side and kind of do the same thing. So we take some off the top for the red square, take some off the right for the blue square, take some off the bottom for the green square, take some off the left for the yellow square, and usually then it ends up of you just use the final bounds for whatever else you have left. So our violet square is what's going to be in the center after everything has been chopped off. So this will give it, it's kind of like if you were to apply margins to each side of your parent bounds and then set the violet square from that. But here it's where we're taking margins as their own individual sections for components, and they can be different sizes. So it basically looks like this. We chop off, and it's important to note that when you do that, so this red square was first, it got all of that. I think the blue square is second. When the blue square is up, because you removed from top, it's now going to be shorter. So you have that much height to work with, and still all of this, width. So then we remove from there, and we have that much left. And after that, we have the sum of these three rectangles is what we have left. So then we just start chopping away at that. And then obviously we can apply some padding if we're reducing the rectangles anyway. And once you do that, basically we just get an optional little border around every component, so that we have some margins to keep in between them. And this usually works out pretty well. It's what we use for our plugins. It just gets kind of finicky of like, okay, we have to, position this and just randomly start translating and applying some padding because it doesn't quite look right. And we don't want to completely center it. We would just kind of want to visually center it and get it close. So you might end up with like, take some chunk off of one of the sides and then pad it and then maybe translate it a little bit or something and that kind of stuff. So it still can end up like that. And usually then it gets a little weird because you just have tons of like, this call, if you're doing a whole bunch of stuff, it's like reduced and it's translated and like 50 different operations that you're doing every time or something. So that can still be less ideal, but it's definitely a better way to lay things out than to manually go in by hand and try and place everything in the right place. Are there any questions so far? Cool. So the last two implementations are newer features in JUCE that come from the web dev side. So if anyone's familiar with web development, there are the Flexbox layouts and the grid layouts. The first one that we're going to go over is Flexbox, and it allows you to just dynamically set layouts along a given axis. So if you have, in our case before, where you want to split something up into sections of 5 across the whole component, you can do that a little easier with the Flexbox, as long as you just set that up in the right way, and if you're doing it in the resized method as well. So it's great because then you basically just give Flexbox, here's all of my items that I'm going to do, here are all the properties for every item, and here's the full layout, like go apply the bounds to all that, and it'll just run it'll calculate all of it for you, and then also apply the bounds to every child that you associated with the items. But it cannot handle 2D like grid layouts. It kind of can, because when you give items to the Flexbox, you can say like, this item controls another Flexbox, so it will like set the bounds and then call the Flexbox layout to then go in and set all those. But that gets a little clunky too, so it's usually it's something of a little bit of each method, so you might like chop off a section and then like do just that section using Flexbox if it's like some kind of title bar or something. Or if you're doing some kind of grid later on, you can chop off that section and like apply like a grid layout for all the components in that section. But yeah, we go into the example for that. And this, I would recommend if you guys want to start using this, like, there's 2 other tutorials that kind of cover this a bit more, because there are just tons and tons of properties for the Flexbox. The Flexbox itself doesn't have a ton, but the Flex item, which is actually what you're associating each component with, you can go in and just set grow and shrink properties and basis and alignments and like minimum, maximum width and height and margins and all kinds of stuff. And in the Flexbox, it can like have its own alignments and justification and all that. And that really applies if you are doing layouts where you might have something that is like, I want this slider on screen and it's going to be like this size, but I'm going to position it based around all of the other content that's in there. So you could say like, okay, this slider gets, a section that's this big, but the slider's only this big, or we're going to align the slider like top left or something. And basically it's kind of like all the text stuff where you can do all crazy text layouts based on the given text size you're trying to draw. Same thing here, where you can do all kinds of justification and alignment and everything if you have components that are not filling up the full bounds that they're given. And in our example, we basically, and they actually do some of it here, where it's like these sliders, there's a lot more bounds than they have, especially this where it's going straight down. It will just align all these center because they specified that, but they each are getting like a full chunk of the size. But they don't necessarily have to be as tall, as a fifth of the full window height. It can just be that they're only, this tall really, and they're just centered within the layout section that they're given. So for the example, it's a pretty simple demo just of splitting that up into the sections. So all we really did was just add our squares in again, set a size, and in scroll is getting crazy. In the resize method, we create a flex box. Basically, it just has a couple members. It's pretty easy to work with, really. Just stack allocate it whenever you need one. Here is a little if-def stuff to flip around directions. So if 0, if 0. Here we're really just going down to here, and we're using row by default, which you saw since they went, across the x-axis. So in our logic, we just grab each child component. We're going to grab a flex item and give it to the flex box each time. And what we're going to say is that each item should be allowed to grow as much as it needs to fill up the section that it's allotted when the flex box runs its layout. So here we just assign that to 1 so that every square is allowed to take up the full size of the section that it's given. And we set an associated component, which is going to be a pointer to a component. So the flex item, when it has its bounds set, it will know to go to that associated component and say, okay, now you set your bounds as well. And similar to our last layout, we also have margins. And the margins can apply to any side. So the item itself, margin here, you can set like a specific, the top has a margin of 5, the right and left have a margin of 10, and the bottom has a margin of 0. So they're specific to each side of the rectangle itself. So we go through, and the flex box has an array called items, which is basically right here. It's just an array of flex item objects. So you can add into that, reorder them, do whatever you want to it. It's just there for you to use. So in our case, we just add a flex item. Flex item is just a struct, so it just copies it over. So it'll copy the pointer, copy over the flex grow property, all that stuff. And then we tell the flex box down here to perform the layout. So it will go through for every item in that array, figure out, okay, what are my properties that I need to actually create this layout, and then start like chopping up the sections and start applying the sections to those flex items. And we can see that here, if we grab this, we can see that it dynamically will update once we're resizing. So we always get full height, and then they split it up into 5s for however wide this is. And then we can also add the margin over to the flex items. Rebuild. Capitalize the I. There we go. And so each of them now has a margin of 10, right?
Yeah, so they have a margin of 10 in between every item. So it'll always keep that 10 pixels between the items, which means any space left over, that's what's going to be assigned to the actual width for each one. So you can see once they get pretty small at these smaller ones because we are saving, like 60, 1, 2, 3, 4, 5, 6, 60 pixels across. So then we only have a little bit left by the time, we're down to this much space. You can also see that it will let you, so we're down here, we're using row. There are row reverse and column reverse methods as well. So if we use row reverse, it will just flip around how it's deciding to lay those out. So you can just easily say, everything I added, actually I wanted that the other way around or something. It will just flip that around for you. The flex items, though, they have an order integer associated with that struct that you can set that, and if it's not 0, then you can specify a specific alignment. So, for instance, we could say, even though we're adding it in this order, this could be the middle one, this could be the first one, the pink one could be the third one or something, if we were to specify that order member for each flex item. And that's useful. That's especially useful when you already have layouts set up that are using Flexbox, and a client is like, hey, can you move these around? Instead of having to say, oh God, that's going to be an hour ordeal now of trying to fix all the positions, just set the order of the items. So even if you're using like layouts that are in grids or aligned to columns and stuff like that, this makes it so much easier than trying to do it any other way, even easier than the rectangle slicing, because once your layout is there, it's super easy to just manipulate, say, okay, the order is completely changing and we're going to add some margins to it. Actually, we want this reversed, actually we want these justified over to the right or something. So working with that is a lot easier. It just really depends on whether or not you need that much of a dynamic layout versus if it's just easier to not set up all this extra Flexbox stuff and just start cutting out rectangles. But if you need grids, then it kind of gets a little bit further and you have to use the grid implementation instead. But yeah, I would highly, highly recommend this over manually positioning things, if you have a need for this kind of thing. Does anyone have any questions about Flexbox stuff? Cool. Brings us to the last layout system, which is Grid, which is also part of WebDev. It's in CSS3 stuff. It's pretty much the same in principle in that the grid will take whatever kind of absolute size is, take those, whatever it has left to work with, it will just start applying that dynamic size to the components and stuff. It has a lot more setup, and honestly their API is extremely confusing to work with. I guess not extremely, but once you're getting into it for the first time, it's just so many different properties and things that are there, and it's just hard to get something quick to set up. But it will let you do a 2D grid. Each row and column can have a specific size, so it's like if you went into Excel or something and started messing around with every, the B column will be this wide and the number 5 row down here or whatever is going to be this tall, and you can just start manipulating it that way where everything gets its own size. But it allows for absolute sizes of the components within that, or dynamic sizes. And you can also just allow the rows and columns to be specifically absolutely sized or dynamically sized as a fraction of however much free space is left when you're doing the layout. So at least the last example, which is pretty basic one of grid. There we go. Same thing. We got all the squares again. This talks about, in the comments, there's some more info on how it works and how, the layout is structured to go through those absolute positions and then take whatever free space is left and use those sizes. So here we create a grid. Same kind of deal where we can have gaps, which are like the margins, but it'll be between each section of the row and column. Our default here is that we assign the auto rows and auto columns sections, and we just say each row gets one fraction of free space. So if we have 5 rows, they each get a fifth of the total size. Same for the columns. So basically, we're just splitting up the whole thing into an equally sized grid of however many items we're going to have. We go through, and we create a grid item for each child. We set the associated component again, and we set the area. So when you're working with a grid, the area can be defined in a few ways. Here, it's going to be the ID of the actual row and column that we want to use. So we're going to say that each one, we increment the row and the column. So they're just going to be dotted down in a diagonal line across the grid. But you can also set areas based on name. So if you have some weird complex layout, you can actually name the areas, like the starting and end regions, and say this goes directly into this region, without having to say okay, well, it's actually number 5 row, number 7 column kind of thing, and it's going to extend out to this number and that number. So that makes it a little bit easier, but it's also a lot of setup. So it kind of depends on how complex this needs to get, and usually it's the case where this would be really helpful if you had tons and tons of components that were all in one child and everything was just laid out on that top level. But usually you don't operate like that. So the grid kind of gets into when you actually need to use this or not. Usually I just end up making hierarchies, and every this section goes and lays out its components, and it's easy enough to just say okay, it takes this much off the top and it puts a button there, and it keeps doing the same around. So the grid can be a little bit overkill. I have only used it once, and it was actually for that layout thing I mentioned, where I could specify the grid type layout and start laying out things just dynamically. But it's still it's a lot of code that you're relying on, I guess, so to speak. But same kind of deal. We perform the layout using the full bounds of our parent. Basically this, I probably should have drawn a background for this white square. But our grid is split up equally. So we have 4 rows and 4 columns, and each one of these, the area is going to be added each time. So 1, 2, 3, 4. And what we can do then, if we know we're going to have that many items, we can add some template rows and template columns. And this is where it kind of gets into setting up your own dynamic grid layouts. The template rows and columns use grid track info struct, which let me open that up real quick. Which basically you can make the track info as a pixel size, as a fraction of free space, and you can actually give it those names I mentioned. So you could give it a starting line to use, and or an ending line, and or use a pixel or a fraction of free space. So it's all up to how you need your layout to be set up. A lot of the times it kind of comes down to just everything's going to be a fraction of free space. I just want a grid that splits up my main component into equal grid of equal size for all the things, and just put them all in there. Especially if it's a drum pad or sequencing kind of stuff where everything's just always in some sort of uniform grid anyway. But if you need stuff to be in specific sizes, like, these tracks are going to be this pixel size all the time, and then the rest of it is all just fractions of how much free space is left, these will let you do that. So basically, we go through the rows and we say the first row gets 2 fractions of the free space. This one gets 1, this one gets 3, this one gets 1, and then these all get 1. So if we enable that, it's basically like I described before, where you start resizing the columns and stuff of the Excel spreadsheet. This one will get 2 fractions of free space. This gets 1. This gets 3, and this gets 1. So it'll actually take it into 7 spaces, basically, and divide those up and then allot them to however many the template row had. So in our case, 2, 1, 3, 1. And then the grid template columns, they're all the same. So we kept those, and they're still split up into 4s. But we can change how the height of each row actually appears. And these will all be based, since they're on fraction of free space, they'll be based on the height of the actual parent component. So we can just resize this, and it'll know how to calculate the bounds and set everything appropriately. I think we also had row gap, so you can specify, turn this back off. You can specify a row gap and a column gap. So if you want things to be spaced out, you can do that. So now we have some gaps in between each column and in between each row. Does anyone have any questions about grid layouts? Cool. That is the last example, and the only thing left is I just have a few performance tips and just things to look out for specifically audio software, because in audio software there's going to be a lot of moving parts on the screen at any given time. Meters, RTAs, like EQs that you're moving around and the curve draws with it, that kind of stuff. So like I mentioned, a lot of the repaint calls will be thrown away if you start doing too many of them. So if you are doing something like filling out some complex data, for example, in our graphs when we're doing the EQ curves, we have to go and calculate that curve like every single time that a band is changing around. But if you do that where, okay, we're going to calculate the whole curve again and then call repaint, the user's not going to see that if bullet point 2 happens, where the OS throws away a call, but it did all of the work to still make the curve shape for you. It just didn't draw it to screen. So a good way to do that is if you're working with that kind of data where we need to update this and the user needs to see it, just do the updating in the repaint, sorry, not the repaint, but the paint method itself. So the very first thing that happens when you actually know you're repainting the component is you update that data, then you go through and draw it. So that way you're not wasting extra effort if you're calling repaint a bunch and the OS is like, we're not going to repaint you. You're doing more work ahead of time that's not being seen. So that's more CPU usage that is being eaten up for things that are just useless at that point. And the OS is then going to say, okay, well now you're increasing CPU usage, so we're going to deprioritize more of your repaint calls, and then everything just looks horrible, basically. Or gets super, super slow, and then people complain. Always use components. I mostly say this because I wrote some stuff that had a bunch of moving parts on the screen, but I was managing that myself. So little pieces that the user could grab and drag around and stuff, and I'm like, oh, well, I don't want to repaint the whole thing every time. I only want to repaint the sections. So it was okay, we have to repaint the old part, repaint the new part. Once you do that, the OS starts throwing away repaints again. You have a copy of okay, this thing was here and now it's here, but it didn't fully clear out the old graphics. So you get weird fragmenting and stuff that's you drag something across and suddenly there's all these little glitchy lines across your component. So, and when you get to that point too, if you make that kind of thing, it already just is
like doing a component hierarchy. So it makes more sense to just split each part of it into its own component, and especially do the behavior specific to each part in each component. So the little piece that you can grab, like that should respond to a mouse event. It should be able to be moved around and dragged and stuff. And it should handle repainting itself. This is especially true if you have things like in audio that are going to be moving around a lot, and especially if they're repainting themselves on top of other components. Because then you can use things too, like setting things opaque. So it's not, if that component's repainting itself a lot, you don't have to like mess around with repainting the background in the parent. And basically that whole painting hierarchy will just handle everything for you, and it will be a lot less headache. And just always draw as little as needed. But some of these have an asterisk next to them, or they should anyway. So ensure the proper bounds and clip regions. Like make sure that when you're drawing within the bounds, and you're not just like saying, hey, there's like 20 shapes off here that I should draw, because it will still go take all those shapes and like flatten the paths and like try to actually use them. Basically all for nothing, because it will not be put in this actual pixel data. But the clip region stuff, don't go too crazy with it, because that whole state stack stuff can be a little heavy to keep like popping state, pushing state, like all that. So sometimes if it's like, okay, I'm gonna like, reduce the clip region like 5 times over just to draw in this little square and stuff, that's kind of more wasteful than just drawing, say, okay, I'm just gonna draw a square and it's in this region. I don't need to like force myself to be within that bounds. Same thing as before, cache complex graphics into like off-screen buffers, or use components buffered to image stuff. This is especially true if you do things like drop shadows and glows and things like that. JUCE comes with, I think I mentioned before, it has drop shadows and glows, and I think image blurs as well. But all of those operate on the pixel data. So you have to pass it an image. It makes some sort of convolution kernel, basically, and then runs all that pixel data through that. And if you're doing that every time, that's going to be very expensive, especially because when it runs that, it's going to give you back like a copy of the image too, for some of these. So it might end up copying the whole image, applying the effect to it, giving you that back, so now you have 2 copies and all this work that was done.